What if everything around us, every galaxy spinning in the dark, every particle dancing at the quantum level, every law that holds reality together, wasn't programmed by anyone, but simply computed itself? No designer, no outside coder, no grand blueprint, just the universe following its own embedded rules, calculating its way into existence moment by moment. This idea might sound like something from the farthest edges of science fiction, but it's actually one of the most compelling mysteries being explored by physicists and philosophers today. It touches on questions we've all asked at some point. Why is the universe the way it is? How does something as complex as life, or consciousness, or the cosmos itself come into being without any guiding hand? In this video, we're going to venture deep into that mystery. We'll explore how natural laws act like built-in algorithms, how fundamental constants set the rules of the game, and how emergence allows simplicity to blossom into breathtaking complexity, all without a programmer calling the shots. We'll travel from the subatomic world, where particles exist in ghostly superpositions, to the vast scales of galaxy clusters and cosmic webs, uncovering the hidden computations that shape everything we see and everything we don't. This isn't just about physics or math, it's about reimagining reality itself as one continuous, self-solving equation. You're about to embark on a journey that will challenge how you see existence. By the end, you may never look at the night sky, a falling leaf, or even your own thoughts the same way again. Because if the universe truly calculates itself, that means we, our minds, our memories, the world we experience, are all part of that magnificent, unscripted computation. So settle in. Let's explore together how the cosmos might not need a creator because it is, in every sense, its own computer. But what if this self-calculating universe isn't just a collection of equations, but something more alive, more organic? To explore that, we need to start not with physics, but with biology. In the 1970s, two Chilean biologists, Humberto Maturana and Francisco Verla, were studying perception and cognition when they stumbled upon a revolutionary idea. They asked a simple but profound question: what is the fundamental characteristic of a living thing? Their answer was autopoiesis, a word meaning self-creation. An autopoietic system is a network of processes that produces its own components, and those components, in turn, continuously regenerate and sustain the very network that produced them. It's a closed loop of self-maintenance. Think of a single cell. It takes in nutrients, processes them, and uses the energy to build and repair its own structure, its membrane, its organelles. The cell's boundary isn't a wall built by someone else. It's built by the cell itself from the inside to maintain its own existence. It has no boss, no external foreman issuing orders. It operates solely through a web of internal, self-referential processes. Now, take that concept and zoom out, way out. Look at a star. A star is born from a collapsing cloud of gas and dust, governed solely by gravity. As it condenses, the immense pressure and heat at its core trigger nuclear fusion. This fusion process releases energy, which creates an outward pressure that counteracts the inward pull of gravity. The star has, in a sense, built its own stable equilibrium. It generates the very forces that sustain its structure for billions of years. It is a self-creating, self-maintaining furnace. It doesn't need an instruction manual. It follows the simple, embedded rules of physics, and in doing so, it organizes itself into a complex, enduring entity. The same principles can be seen in the majestic spiral arms of a galaxy. Each galaxy is a gravitational dance of billions of stars. a structure that emerges and maintains its form not from a top-down design, but from the local interactions of all its components obeying a few basic laws. This is the powerful leap in thinking. If a single cell and a swirling galaxy, two things unimaginably different in scale, can both exhibit this behavior of self-organization and self-perpetuation, then perhaps the principle is universal. The cosmos itself might be the ultimate autopoietic system. The laws of physics, gravity, thermodynamics, quantum mechanics act as that foundational set of rules. The universe, in its earliest moments, began with a set of initial conditions and these immutable laws. From that starting point, it has been computing its own state forward, moment by moment, creating the galaxies, stars, planets, and even life as emergent products of its own ongoing process. There is no need for an external programmer to write the code for a star or design the pattern of a galaxy cluster. The code is already embedded in the fabric of reality, and the universe executes it autonomously. We are not looking at a clockwork universe wound up by a watchmaker. We are witnessing a living, computing, self-organizing system that is, in every sense, creating itself as it goes. But if the entire cosmos is a self-sustaining system operating on its own internal logic, then what is the fundamental nature of that logic? This brings us to a breathtaking idea, one that pushes the very concept of reality to its limit. Imagine that the universe isn't just described by mathematics, but that it is mathematics. This is the core of the mathematical universe hypothesis, championed by physicist Max Tegmark. He proposes a radical shift in perspective. Our physical reality isn't merely modeled effectively by math. It is, in its entirety, a mathematical structure. Think about that for a moment. The chair you're sitting on, the air you're breathing, the neurons firing in your brain according to this view. These are not just things that can be measured and calculated. They are, in their most fundamental essence, mathematical objects and relationships. The equations we discover aren't just handy tools we invented. They are the actual blueprints of existence, and the constants within them are the immutable properties of this grand structure. This idea finds powerful support in the eerie effectiveness of mathematics throughout the sciences. The laws of physics are not suggestions. They are unwavering rules that hold true from the farthest reaches of the observable cosmos to the quantum foam bubbling beneath our feet. The gravitational constant that dictates the orbit of a planet is the same one that causes an apple to fall. The speed of light is a universal speed limit, an unwavering parameter woven into the fabric of space-time itself. These aren't laws that the universe obeys, they are the universe. As Tegmark himself states, our external physical reality is a mathematical structure. This transforms our understanding of the cosmos from a physical machine into an immense dynamic computation. The universe's native language isn't English or Chinese, it's mathematics. Every interaction, from the collision of two atoms to the silent drift of galaxies, is a mathematical operation. The cosmos is not running a calculation, it is the calculation, a single, ongoing equation solving itself across space and time. This perspective completely dissolves the need for an external programmer. In a purely mathematical universe, the code and the output are one and the same. The programmer isn't a separate entity because the program is self-contained, existing necessarily as a coherent mathematical structure. It invites us to see the elegant spiral of a galaxy not as a thing, but as a solution, a beautiful, emergent answer to a set of deep mathematical constraints. It suggests that every possible mathematical structure might exist somewhere in a vast multiverse of realities, each with its own unique set of rules. Our particular universe, with its specific constants and laws that allow for stars, planets, and life, is simply one of many possible mathematical structures that has the property of being self-aware. We are not just observers of this grand computation. We are a part of the mathematical pattern itself, a localized knot of self-referential complexity that has arisen within the equation. This sets the stage perfectly for exploring the realm where this computation becomes its most active and mysterious, the quantum world. This concept of the universe as a self-contained mathematical structure finds its most active and bewildering expression not in the vastness of space, but in the bizarre and counterintuitive realm of the quantum. If the cosmos is indeed calculating itself, then the quantum world is its processing core, where the raw computation of reality happens in real time. Here, the familiar rules of our everyday experience break down completely. Particles like electrons and photons don't exist in a single, definite location with a certain velocity, the way a planet orbits a star. Instead, they exist in a haze of potentiality known as a superposition, a state where they are effectively in many places, or have many possible energies all at once. It's only when we reach out and measure them, when we interact with this quantum system, that this cloud of possibilities collapses into a single, concrete outcome that we can record. This isn't a limitation of our instruments. It's a fundamental feature of how the universe operates at its most basic level. The mechanism governing this strange behavior is the Schrödinger equation. This isn't just any equation. It's the universe's own master algorithm for processing quantum possibilities. Without any external instruction, this mathematical rule dictates precisely how a quantum state will evolve and change over time. It calculates the probability wave, the spread of all potential outcomes with flawless, deterministic precision. There is no programmer deciding which path an electron will take. The equation simply computes the odds for every conceivable path, and the particle's behavior follows this computed landscape of probabilities. The brilliant physicist Richard Feynman captured this computational essence perfectly with his path integral formulation. He proposed that a quantum particle doesn't choose a single path from point A to point B. Instead, it effectively takes every possible path simultaneously, and the Schrödinger equation acts as the calculator that sums up all these histories to determine the most probable final outcome. Feynman himself saw this not as mere analogy but as a fundamental description of nature's process, a view that deeply aligns with the idea of the universe as a natural computer. Perhaps no experiment demonstrates this self-computing nature more clearly than the famous double-slit experiment. Imagine firing a single electron at a barrier with two narrow slits cut into it. On the other side is a screen that lights up wherever an electron hits. If electrons behaved like tiny bullets, you'd expect them to go through one slit or the other and create two clusters of dots on the screen behind the slits. But that's not what happens. When you aren't watching, when you don't have a detector at the slits to see which one it goes through, the electron does something incredible. It doesn't choose a path. It behaves as if it passes through both slits at once, like a wave. This wave of potential then spreads out and interferes with itself on the other side, creating a pattern of light and dark bands on the detection screen, an interference pattern that is the hallmark of wave behavior. This pattern isn't random. It is the direct computed result of the electron exploring all possible routes and the probabilities of those routes interacting. The universe is running a calculation on the fly to determine where that electron is most likely to end up. Each individual electron seems to arrive at a random point, but after thousands of them, the exquisite interference pattern emerges, revealing the hidden probabilistic computation that guided each one. This is the profound insight. At the very smallest scales of existence, the universe is not a static place. It is a seething, dynamic arena of constant calculation. Every moment for every particle, reality is a process of evaluating possibilities, computing probabilities, and resolving uncertainties through interaction. There is no central processing unit issuing commands. The computation is distributed, a fundamental property of matter and energy itself. The cosmos is not being programmed, it is programming itself, one quantum event at a time. And this raises a monumental question. If this is how reality works for a single electron, how do these countless, infinitesimal quantum computations combine and scale up to create the stable, predictable world we see around us, the world of trees, rocks, planets, and people? So if the quantum world is the universe's processing core, where probabilities are constantly being calculated and resolved, we are left with a beautiful puzzle. How does this fuzzy, probabilistic dance at the smallest scales give rise to the crisp, concrete reality we experience, the majestic spiral of a galaxy, the intricate branching of a tree, or even the complex workings of a living cell? The answer lies in a powerful principle known as emergence. This is the astonishing phenomenon where simple rules, followed by countless individual components, collectively give rise to entirely new levels of order and complexity that were never explicitly programmed into the system. There is no top-down design, no master architect sketching the blueprint for a snowflake. Instead, breathtaking complexity emerges spontaneously from the bottom up, through countless local interactions governed by a handful of fundamental laws. We see this principle at work everywhere in nature. Consider a flock of starlings weaving through the sky in a mesmerizing, fluid cloud known as a murmuration. There is no lead bird giving commands, no overall plan. Each bird follows just a few simple rules: stay close to your neighbors, match their speed, and avoid collisions. From this minimal set of instructions, the entire flock moves as a single, intelligent superorganism, creating patterns of stunning complexity and beauty that far exceed the capability of any individual bird. The complex pattern emerges from the simplicity of the rules. This same concept scales up to the very architecture of the cosmos. The vast cosmic web of galaxies, with its great walls and immense voids, didn't form because some programmer placed each galaxy in a specific spot. It emerged from the relentless pull of gravity acting on tiny, random fluctuations in the density of matter in the early universe. Each particle simply followed the local rule of gravity, attracting others, and over billions of years, these trillions upon trillions of local interactions computed the large-scale structure of the entire observable universe. This idea that immense complexity can arise from startlingly simple beginnings is a cornerstone of complexity science. The computer scientist and physicist Stephen Wolfram has been a profound voice in this field, arguing through his work on cellular automata that the universe might literally be a digital computation. His most famous example is Rule 30, a remarkably simple program that determines the color of cells in a grid based on the colors of their immediate neighbors. From this one-line rule, an astonishingly complex and seemingly random pattern emerges as the computation runs row by row. It generates an intricate, jagged tapestry that never repeats itself. Wolfram's revolutionary suggestion is that many of the complex patterns we see in nature, from the markings on a seashell to the turbulent flow of a river, might be generated by similar underlying computational rules of immense simplicity. The universe doesn't need a complex program to create complexity. It can compute intricate outcomes from the most basic principles, simply by letting those rules run and interact over time. This process of emergence is how the universe builds itself. The quantum probabilities computed by the Schrödinger equation provide the raw material, the possibilities. The fundamental forces like gravity and electromagnetism provide the simple, local rules of interaction, and from there the system computes its own future. Atoms find each other to form molecules. Molecules assemble into crystals and proteins. Stars ignite from clouds of gas, and planets coalesce in their orbits. Each step is an emergent level of complexity, each one bootstrapping itself from the level below without any external guidance. The universe is a cascade of emergence, where each new layer of complexity becomes the foundation for the next, all computed from the bottom up. It is a testament to the power of simple rules, iterated over vast scales of space and time, to create a reality of boundless richness and wonder. And this entire magnificent, self-assembling process is driven forward by a fundamental, irreversible force that gives direction to the cosmic computation, the relentless increase of entropy, a concept deeply intertwined with the very nature of information itself. But this magnificent process of emergence, this bottom-up computation that builds galaxies and life, doesn't happen for free. It is powered and given direction by a fundamental, one-way street in the cosmos, the relentless and inevitable increase of entropy. In our everyday language, we often think of entropy as disorder or chaos, a messy room, a scattered deck of cards. But in physics, and especially in information theory, entropy is something far more profound. It is a precise measure of uncertainty, of the number of possible ways a system can be arranged. A system with low entropy is highly ordered, with very few possible configurations. Think of a brand new deck of cards perfectly sorted by suit and number. There's essentially only one way for it to be in that state. A system with high entropy, by contrast, is disordered, with a vast number of possible configurations like that same deck after a thorough shuffle. The second law of thermodynamics states that the total entropy of a closed system, like our universe, can never decrease over time. It only increases or stays the same. The universe is constantly moving from states of lower probability to states of higher probability, from order to disorder. This might sound like a grim winding down of the cosmos into a featureless, lukewarm soup, a fate known as the heat death of the universe. But here's the incredible twist. This inevitable slide into disorder is precisely what drives the universe's capacity for computation and creates the conditions for complexity. The great flow of entropy establishes thermodynamic gradients, differences in energy and concentration, like the heat difference between a hot star and the cold void of space. It is these gradients that power every process in the universe, from the nuclear fusion in a star's core to the weather patterns on a planet, and even the electrical signals firing in your brain. A universe in perfect equilibrium with maximum entropy everywhere would be a universe where nothing ever happens. It would be a static, computed answer with no further processing. The ongoing increase of entropy is what provides the energy for the cosmic computer to keep running its next calculation. This deep connection between information processing and physics was cemented by Rolf Landauer in the 1960s. Landauer's principle is a stunningly simple yet profound insight. Information is physical. He realized that the act of erasing information, resetting a bit in a computer from a 1 or a 0 back to a known state, like a 0, is not an abstract logical operation. It is an irreversible physical process that must release a tiny amount of energy as heat into the environment, thereby increasing its entropy. This means that forgetting, the loss of information, has a fundamental energy cost. Every computation, at its most basic level, is a physical process that is subject to the laws of thermodynamics. The universe isn't just performing abstract math, It is physically manipulating information, and that manipulation has tangible consequences, dissipating energy and contributing to the overall arrow of time. This binds the fate of information irrevocably to the fate of the cosmos itself. This brings us to the heart of information theory pioneered by Shannon. He defined information not as meaning or data, but in a brilliantly counterintuitive way as the resolution of uncertainty. The more uncertain you are about an outcome, the more information you gain when you learn what it is. A coin flip has higher uncertainty, and thus conveys more information when you see the result than being told the sun will rise tomorrow, which is a near certainty. From this perspective, the universe is a grand engine for processing information. It begins in a state of extremely low entropy, a very specific, highly ordered configuration after the Big Bang, which represents a state of incredibly high uncertainty about how it will evolve. As time moves forward and entropy increases, the universe resolves that uncertainty. It computes its own future state by exploring possibilities, making choices at quantum junctions, and building complex structures. Every star that forms, every planet that cools, every molecule that replicates is a step in this cosmic computation, a localized process where information is being physically processed and uncertainty is being resolved within the vast entropic flow. The universe isn't just computing, it is learning about itself one bit at a time. But if the cosmic computation is powered by the flow of entropy and information, what are the actual, unchangeable rules of this grand game? To answer that, we must look at the fundamental constants of nature. These are not mere numbers we've measured. They are the universe's immutable algorithmic parameters, the hard-coded values in the source code of reality that dictate how every single interaction must play out. Think of them as the ultimate settings in a cosmic simulation, except there is no outside user to adjust the sliders. These values are fixed, and they set the stage for everything that is possible. Consider the speed of light in a vacuum, universally denoted by the letter c. It is not merely the velocity at which light happens to travel. It is a fundamental conversion factor between space and time itself, the ultimate speed limit for causality in the universe. Nothing, no particle or ripple of information can exceed this speed. This constant, approximately 299,792,458 meters per second, is the rule that governs the very structure of spacetime, determining how distances contract and time dilates for moving objects. Then there is Planck's constant, h, a tiny number that defines the granularity of the quantum world. It sets the size of the quanta, the indivisible packets of energy that can be exchanged. This constant is why energy levels in an atom are discrete, like rungs on a ladder, and not a smooth ramp. It is the parameter that tells the universe, this is the smallest possible unit of action here. Without it, reality would be a continuous blur, not the pixelated, quantized world we actually inhabit. These constants work in concert to create the laws of physics as we know them. But perhaps the most mysterious and suggestive of all these parameters is a pure, dimensionless number known as the fine structure constant. Unlike the speed of light or Planck's constant, its value does not depend on any system of units. It is simply a ratio, approximately 1/137, that emerges from the relationship between other constants, specifically the charge of the electron, the speed of light, and Planck's constant. This number, often represented by the Greek letter alpha, is a measure of the strength of the electromagnetic force. It dictates how tightly electrons are bound to an atomic nucleus, which in turn determines the stability of atoms themselves and the nature of all chemical bonds. If this number were even slightly different, the universe would be unrecognizable. A fraction larger, and stars would burn through their fuel too quickly for life to emerge. a fraction smaller, and complex molecules might never form. This profound sensitivity raises one of the deepest questions in all of science. Why do these constants have the precise values that they do? Are they arbitrary, frozen in place by some random chance during the birth of the universe, a cosmic roll of the dice that just happened to come up lucky for us? Or are they necessary, the only possible values that could allow for a stable, coherent, and self-aware universe to exist at all? This is the puzzle of fine-tuning. If these algorithmic parameters were different, the cosmic computation would simply fail to produce any interesting complexity. It would either fizzle out immediately into a uniform haze or collapse back on itself almost instantly. The fact that we are here to ponder the question suggests that our universe's particular set of constants is at least one that permits the long, intricate computation of galaxies, stars, planets, and life. They are not just numbers in an equation, they are the foundational settings that enable the entire emergent cascade of reality to compute itself into existence. They are the universe's built-in programming, and their precise values are the reason anything exists at all. Yet among all the fundamental forces, there is one that stands apart, not just for its universal pull, but for its profound role as the universe's master architect. We think of gravity as the force that makes apples fall and planets orbit, but to see it merely as a force is to miss its true, deeper nature. Gravity is the cosmos's primary computational mechanism, the grand algorithm that sculpts the very stage upon which all other processes play out. This revolutionary view begins with Einstein's monumental insight. Gravity is not a force that magically acts across empty space. Instead, it is the curvature of spacetime itself, a geometric warping caused by the presence of mass and energy. Think of spacetime not as a static, empty container, but as a dynamic, flexible fabric. Place a heavy object like a star on this fabric, and it creates a depression, a gravitational well. The path of any other object, a planet, a beam of light, is then determined simply by following the contours of this curved geometry. It's not being pulled, it's rolling downhill along the path of least resistance, computed for it by the shape of space. This geometric computation is captured with breathtaking elegance in Einstein's field equations. These are not simple formulas. They are a complex set of interlinked differential equations that form the universe's own instruction manual for calculating the geometry of spacetime from any given distribution of matter and energy. The equations work both ways. Matter tells spacetime how to curve, and the curvature of spacetime tells matter how to move. It is a continuous, self-consistent feedback loop, a computation that the universe is running at every single point, at every moment, to determine the structure of reality itself. There is no programmer manually adjusting the curvature. The equations themselves, acting on the initial conditions of the cosmos, compute the entire history of its expansion, the formation of its galaxies, and the orbits of its world. This is gravity in its ultimate role, not as a simple force, but as the dynamic, geometric computation of the cosmos's evolving shape. Nowhere is this computational power of gravity more extreme and more mysterious than in the formation of a black hole. When a massive star collapses under its own immense weight, the curvature of spacetime it creates becomes so severe that it pinches off from the rest of the universe, creating an event horizon, a point of no return. Within this region, the gravitational computation becomes so intense that our known laws of physics break down. A black hole is, in a sense, the universe's ultimate information processor, but it presents us with a profound paradox. According to quantum mechanics, information cannot be destroyed. Every particle that falls in carries information about its properties. But according to general relativity, anything that crosses the event horizon is lost forever. crushed into a singularity of infinite density. So, what happens to that information? Is it erased, stored on the surface of the event horizon, or processed in some way we cannot yet comprehend? This black hole information paradox is one of the greatest unsolved problems in physics, and it highlights the limits of our understanding of how gravity computes reality in its most extreme environments. This leads to a radical and compelling idea that pushes our understanding even further. What if gravity isn't even a fundamental force at all? This is the view proposed by theorists like Eric Verland, who suggests that gravity is an emergent phenomenon. It doesn't exist at the most basic level of reality, but arises from something even more fundamental, entropy and information. Verland's theory draws a stunning connection between gravity and thermodynamics, the science of heat. He proposes that gravity is a consequence of the universe's natural tendency to maximize entropy. Much like the pressure in a gas isn't a fundamental force, but emerges from the collective statistical behavior of countless molecules bouncing around. In this view, the force we feel as gravity is actually an entropic force. It emerges from the changes in information associated with the positions of material bodies. When an apple falls, it isn't being pulled by the earth. It is moving towards a state of higher entropy, following the statistical tendency for the universe to become more disordered. The curvature of spacetime itself would then be a kind of illusion, a macroscopic description that emerges from microscopic degrees of freedom we have yet to fully describe. This perspective is revolutionary because it completely demotes gravity from its status as a fundamental force. It suggests that what we perceive as the relentless, geometric computation of spacetime is actually a side effect, a statistical outcome of a deeper, information-theoretic process happening at the quantum level. Gravity would be the universe's way of keeping its books balanced, of ensuring that entropy increases, and it does this not through a pre-written program, but through the collective behavior of countless underlying components. This shows with stunning clarity how gravity performs its cosmic calculations, shaping galaxies, bending light, and governing orbits without any need for a central programmer. It emerges, it computes, and it builds, all as a natural consequence of the universe's foundational drive toward disorder. And this intricate dance of computation, whether emergent or fundamental, operates within a framework that is at once perfectly deterministic and utterly unpredictable, a domain governed by a fascinating blend of rigid law and sensitive chaos. This brings us to a fascinating and seemingly paradoxical feature of the universe's self-calculation, its profound sensitivity. We've seen how the cosmos operates on precise, deterministic rules, from the unwavering equations of gravity to the statistical certainty of thermodynamics. It would be natural to assume that with perfect knowledge of these rules and the current state of everything, we could compute the future with perfect accuracy. This was the dream of classical physics, a clockwork universe where every tick dictated the next talk. But the reality is far more interesting and far less predictable. The universe is a deterministic system, but it is not a predictable one. This is the breathtaking domain of chaos theory. Chaos theory reveals a universe where outcomes are exquisitely sensitive to their starting conditions. The most famous illustration of this is the metaphorical butterfly effect. The idea that the minute air disturbance from a butterfly flapping its wings in Brazil could set in motion a chain of events that ultimately amplifies into a tornado in Texas. This is not a suggestion of magic or randomness. It is a statement about the nonlinear nature of reality's computation. The equations governing whether systems are perfectly deterministic, they don't rely on random dice rolls. But because the atmosphere is a complex, interwoven system, tiny, immeasurable differences in initial air pressure, temperature, or humidity are not simply smoothed out. Instead, they are magnified exponentially over time through countless feedback loops. The system is computing its future state with absolute mathematical precision, but our inability to measure every single variable with infinite accuracy means that beyond a very short window, its future becomes fundamentally unpredictable. The computation is too complex and too sensitive for any practical forecast. This behavior isn't confined to weather. We see it in the orbital mechanics of our own solar system. While the orbits of planets appear stable over human timescales when projected over millions of years, their gravitational interactions create a chaotic system. Precise calculations of Earth's exact orbital eccentricity or axial tilt too far into the future become impossible because the tiniest gravitational nudge from a passing asteroid or the subtle pull of a distant planet can, over eons, send the calculation down an entirely different path. The universe knows the path, it is computing it perfectly, but from our limited perspective, the outcome appears random. Yet within this chaos there is a hidden order, a beautiful structure to the madness. This is perfectly captured by the Lorenz Attractor, a mathematical model developed by meteorologist Edward Lorenz. When you plot the solutions to his simplified weather equations, they don't form a neat, predictable loop or settle into a single point. Instead, they trace out an astonishingly intricate double-looped pattern that resembles a pair of butterfly wings. The path of the system on this attractor is chaotic. It never crosses the same point twice, and its future position is unpredictable. But it is also bound. It never wanders off into infinity. It is constrained to forever dance within this beautiful, finite structure. It is a powerful visual metaphor for the universe's computational nature, wildly unpredictable in its specific details, yet perfectly orderly and bounded in its overall behavior. It is deterministic chaos. This reveals a crucial insight about our self-calculating cosmos. The unpredictability we see is not evidence of true randomness or a lack of rules. It is evidence of immense, layered complexity. The universe is computing outcomes without any programmer injecting randomness. The apparent randomness emerges from the mind-boggling complexity of the computation itself. It is a system that is predictable in principle if one had godlike knowledge of every variable but utterly unpredictable in practice for any entity within the system. This means that the future is not written, but it is being written, calculated moment by moment through the unfathomably complex interaction of every particle and force, each step perfectly determined by the step before. This intricate dance of deterministic chaos provides the creative friction, the unexpected turns and possibilities that allow for novelty and true complexity to emerge. It is the mechanism that prevents the universe's computation from being a boring, predetermined script and instead makes it an unfolding, creative, and genuinely surprising story. And this story finds its most complex and fascinating expression in the entities that have evolved within the computation, living organisms themselves. And so we arrive at the most complex and awe-inspiring output of this cosmic computation, life itself. After exploring the fundamental algorithms of physics and the emergent chaos of complex systems, we find that living organisms represent perhaps the most sophisticated subroutines running within the universe's grand program. A biological cell is not merely a passive object being acted upon by physical laws. It is an active, information-processing entity that embodies the principles of self-organization and computation we've seen at cosmic scales. Within every living thing, from the simplest bacterium to the most complex human brain, exists a breathtakingly intricate network of molecular machines that sense, process, and respond to their environment, all following instructions written in a universal language, the genetic code. At the heart of this biological computation lies the most famous algorithm in the natural world, DNA. This double helix molecule is far more than a static blueprint. It is a dynamic, executable program that computes the development and functioning of an organism. The sequence of nucleotide bases along its length adenine, thymine, cytosine, and guanine forms a digital code of astonishing density and precision. This code is not merely descriptive, it is prescriptive. It contains the instructions for building proteins, the molecular workhorses that carry out virtually every task within a cell. But the computation doesn't end there. The genome also includes regulatory sequences that act like logical switches and loops, controlling when and where genes are expressed. This creates a complex network of feedback and feed-forward controls, a biological circuit that computes the appropriate response to internal and external signals. When a cell divides, this program replicates itself with remarkable fidelity, yet it also allows for random mutations, tiny errors in copying that introduce novel variations into the code. This combination of precise replication and controlled randomness is the engine of evolution, allowing life to compute new solutions to the perpetual challenge of survival. This computational view of biology finds its most powerful expression in the human brain, arguably the most complex information processing system we know of in the universe. Your brain is not a passive recipient of sensory data. It is an active inference engine, constantly generating predictions about the world and updating its models based on sensory input. This happens through a vast network of approximately 86 billion neurons, each forming thousands of connections with its neighbors. These neural networks do not operate with the crisp, binary logic of a digital computer. They perform a kind of wet, analog computation based on the strength of synaptic connections and the firing rates of neurons. When you see a familiar face, hear a melody, or make a decision, it is not the result of a single calculation but the emergent outcome of countless parallel processes spread across this immense network. Your brain is computing your reality moment by moment, integrating past experiences with present sensations to guide your actions. It is a biological computer of such sophistication that it has developed the capacity to reflect upon its own existence and even to ponder the computational nature of the universe that gave it birth. This perspective leads us to a rather humbling yet fascinating conclusion about our place in the cosmic order. The renowned evolutionary biologist Richard Dawkins captured this idea with striking clarity when he wrote, "We are survival machines, robot vehicles blindly programmed to preserve the selfish molecules known as genes." From this viewpoint, an organism is not the ultimate purpose of the genetic program, but rather its temporary embodiment, a sophisticated vehicle constructed to ensure the replication and propagation of the genetic information it carries. Our bodies, our instincts, our drives, even our capacities for love, curiosity, and creativity can be seen as computational strategies evolved to solve the problem of survival and reproduction in a complex and changing environment. This does not diminish the wonder of life, rather it reframes it. We are not separate from the universe's computation. We are a particularly intricate and self-aware manifestation of it. Life becomes a magnificent subroutine within the cosmic program, a process that takes the raw materials and energy flows of the planet and computes increasingly complex forms of order, consciousness, and culture. This biological computation operates on multiple timescales simultaneously. On the fast timescale of an organism's lifetime, neural networks compute perceptions and behaviors. On the slower timescale of generations, the genetic algorithm computes evolutionary adaptations through natural selection. And on the grandest scale of all, the biosphere itself functions as a planetary-scale computational system, regulating atmospheric composition, nutrient cycles, and energy flows in ways that maintain conditions suitable for life. From the molecular machinery inside a cell to the global network of ecosystems, life processes information. It transforms sunlight into chemical energy, environmental cues into adaptive responses, and random mutations into innovative solutions. We are living proof that the universe's capacity for computation extends far beyond the inanimate laws of physics into the realm of purpose, agency, and mind. This realization naturally expands into an even more comprehensive view that perhaps not just life, but everything in existence, from the smallest particle to the largest galaxy, is engaged in a form of information processing. If the biological world is a complex subroutine within the cosmic program, then we must ask a truly radical question. Is this computation limited to life, or is it the fundamental nature of everything? This idea that every single physical process is a form of computation is known as pancomputationalism. It is the view that computation isn't just something the universe does, it is what the universe is at its most basic level. From the gentle arc of a thrown ball to the furious dance of quarks inside an atom, from the silent expansion of spacetime to the firing of a neuron, every event, no matter how simple or complex, is a computational process. Information isn't just being processed in brains and cells, it is the very currency of reality, and its exchange is what we perceive as physics. This perspective elevates information from a human concept to a fundamental constituent of the cosmos, on par with matter and energy. The philosopher Luciano Floridi has been a leading voice in this field, developing a philosophy of information that argues it is a primary, ontological substance. He suggests that the world is not made of indivisible particles in a void, but rather of clusters of information, which he calls informational objects. In this view, a rock isn't just a collection of atoms, it is a highly stable, densely packed informational structure. A sunbeam isn't just energy, it is a flowing stream of informational packets, photons transferring data across the void. This isn't merely a metaphor, it suggests that the laws of physics are, in essence, the algorithms that govern how this cosmic information can be transformed, transmitted, and stored. The universe isn't a machine that processes information. It is an information processing system that we experience as a physical reality. We can find a powerful and intuitive analogy for this in the world of cellular automata, most famously exemplified by John Conway's Game of Life. Imagine a vast, two-dimensional grid of squares, each of which can be in one of two states, alive on or dead off. The entire system is governed by just a handful of simple rules that determine the state of each cell in the next moment based on the states of its 8 immediate neighbors. For instance, a live cell with too few neighbors dies of loneliness. A dead cell with exactly 3 live neighbors springs to life. From these minimal, local rules, an astonishing universe of complexity emerges. Over time, stable structures form. Gliders that slide across the grid, guns that periodically emit new gliders, and even patterns complex enough to function as logic gates, the building blocks of a computer. This entire rich, dynamic, and unpredictable world is computed from the bottom up. There is no central processor directing the action. The computation is distributed across the grid, with each cell and its neighbors performing a tiny, local calculation that collectively generates a global pattern. This is a stunningly accurate mirror of our own cosmic evolution. The universe in its earliest moments might be thought of as a simple, homogeneous grid with a basic set of rules, the fundamental laws of physics. And just as in the game of life, those simple, local rules, iterated over immense scales of space and time, have computed everything we see around us. The formation of the first atoms was a computational event. The gravitational collapse of the first stars was a computational event. The evolution of life and the rise of consciousness are computational events of breathtaking complexity, but they are not different in kind from the rest. They are all manifestations of the same underlying informational process. Pancomputationalism implies that the universe is a computer not in a metaphorical sense, but in the most literal sense possible. The only difference is the substrate. Instead of silicon chips and electrical currents, the universe's computer is built from space-time, quantum fields, and the relentless, algorithm-driven flow of information. This realization forces us to confront profound questions about our own experience within this computation, particularly the nature of two things we hold most dear: our free will and our conscious awareness. If every process in the universe is computational, from the orbit of a planet to the division of a cell, then the most intimate and mysterious process of all our own conscious experience must be part of that same grand computation. This leads us to one of the most profound and challenging frontiers of science: understanding consciousness not as some magical, ethereal substance, but as an emergent property of the physical brain's intricate information processing. We are not just computers made of meat. We are the universe's computation become aware of itself. The raw data of light hitting our retinas, the pressure waves of sound entering our ears, these are inputs. Our brain's neural networks perform immense calculations on this data, cross-referencing it with memories and predictions to construct a stable, useful model of the world. But the breathtaking result isn't just a model. It is the rich, subjective, and deeply personal experience of being the redness of red, the warmth of the sun, the ache of sadness. This is the hard problem of consciousness. How does objective, mechanical computation give rise to subjective experience? One of the most compelling attempts to solve this problem is integrated information theory, or EIT, developed by neuroscientist Giulio Tononi. IIT makes a radical proposal: consciousness is integrated information. The theory starts from the one thing we can all be sure of: we are conscious. From that axiom, it works backward to deduce the physical properties that must be present in a system to generate that experience. Tononi argues that consciousness corresponds to a system's capacity to integrate information. It's not just about the amount of information a system can store or process, but about how that information is woven together into a unified, inseparable whole. A system with high phi, IIT's measure of integrated information, has a cause-effect power upon itself that is greater than the sum of the cause-effect powers of its parts. Your experience of seeing a rose is not just the separate processing of its color, its shape, and its smell in different parts of your brain. It is a single, unified experience where all those elements are inextricably linked. According to IIT, this unity is the hallmark of consciousness. As Tononi himself poetically stated, consciousness is the way information feels when it is being processed. In this view, your mind is not a computer program. It is the specific, complex, and integrated way your brain's circuitry shapes and constrains the flow of information, and that specific shape is the feeling of being you. But this computational view of mind inevitably runs into a classic and powerful thought experiment: the Chinese room, proposed by philosopher John Searle. Imagine a person who speaks only English is locked in a room with a vast rulebook written in English. Through a slot in the wall, people pass in cards with squiggles on them. These are questions written in Chinese. The person inside doesn't understand a word of Chinese, but the rulebook provides meticulous syntactical instructions. If you receive a card with squiggle sequence A, respond by passing out a card with squiggle sequence B. The person follows these rules perfectly, manipulating symbols based on their shape, not their meaning. To someone outside the room, the responses are perfectly coherent and intelligent. it appears that the room understands Chinese. But does the room itself or the person inside actually understand the questions or the answers? Searle argues no, it is merely manipulating symbols without any comprehension. The thought experiment is a direct challenge to the idea that mere computation, the right kind of symbol manipulation, can ever produce genuine understanding or qualia, the raw feel of experience. It suggests that syntax, the rules for manipulating symbols, is not sufficient for semantics, the actual meaning behind those symbols. The Chinese room seems to create a stark divide between the mechanics of computation and the mystery of understanding. However, proponents of computational consciousness offer a compelling counterargument. They point out that the thought experiment misleadingly focuses on a single, isolated component, the man in the room. The understanding, they argue, does not reside in the man alone, but emerges from the entire system. The man, the rulebook, the stacks of cards, and the slots for input and output. In the same way, understanding in a brain does not reside in a single neuron. No single neuron understands the concept of love or beauty. That understanding is a global, emergent property of the entire networked system of billions of neurons working in concert. The room as a whole system can be said to understand Chinese, even if its individual components do not. This debate forces us to ask whether consciousness is a property of the process of computation itself, rather than a property of the physical stuff doing the computing. If consciousness is truly an emergent property of complex, integrated information processing, then it may not matter if the processor is made of biological neurons or silicon chips. If the system achieves a high enough degree of integrated information, subjective experience could, in principle, emerge there too. This ties our most intimate human experience directly back into the cosmos's computational framework, suggesting that we are localized knots of highly integrated information within the universal computation, and that our consciousness is the universe's way of experiencing its own ongoing calculation. This entire cosmic computation, from the quantum dance of particles to the majestic evolution of galaxies, unfolds within a fundamental and often misunderstood framework, time. We tend to think of time as a passive stage, a universal clock ticking away in the background, indifferent to the events playing out upon it. But if the universe is truly calculating itself, then time cannot be a mere backdrop. It must be the most essential resource for that computation, the very dimension across which the cosmic program executes its instructions. Every calculation, every interaction, every emergent pattern requires a sequence of moments to unfold. Time is the currency of change, and without it, the universe would be a single, static, computed answer, a frozen snapshot with no past and no future. It is the medium through which potential becomes actual, where the countless probabilities of the quantum world resolve into the single, consistent history we experience. The direction of this computation is given by one of the most fundamental features of our reality, the arrow of time. Why do we remember the past but not the future? Why does an egg easily scramble but never spontaneously unscramble itself? This one-way directionality isn't just a quirk of our perception. It is a fundamental property of the cosmos, and it is inextricably linked to the flow of information and the increase of entropy that we discussed earlier. The universe began in a state of incredibly low entropy, a highly ordered and specific configuration following the Big Bang. This was a state of immense potential, like a coiled spring or a perfectly sorted deck of cards. The second law of thermodynamics dictates that the universe must evolve toward states of higher entropy, toward disorder and randomness. This inevitable slide is what gives time its arrow. It provides the thermodynamic gradient that powers every process, From nuclear fusion in stars to the electrical currents in our brains, the universe is computing its future states by moving from a state of low probability, the highly ordered early universe, to states of higher probability, a more disordered, higher entropy state. Each computational step dissipates a little energy, increases the total entropy, and irrevocably points the arrow of time forward. This means the flow of time and the processing of information are two sides of the same coin. The universe computes, and in doing so, time moves forward. This leads to a truly mind-bending possibility that emerges from the frontiers of theoretical physics. What if time itself is not fundamental? Our everyday experience tells us that time is a continuous, flowing river, but some of the most promising theories seeking to unify quantum mechanics and general relativity theories of quantum gravity suggest that time might be an emergent property. It might not be a basic feature of the cosmos, but something that arises from a more fundamental, timeless level of reality. Think of it like temperature. We experience temperature as a real, measurable property, but it isn't fundamental. It emerges from the average kinetic energy of countless molecules moving around. In a single, isolated molecule, the concept of temperature is meaningless. Similarly, some physicists propose that time might emerge from the relationships between events or from the quantum entanglement of particles. In this view, the smooth, flowing time we experience could be a kind of illusion, a macroscopic approximation that emerges from a vast network of underlying, timeless quantum computations. The passing of time would then be akin to the changing frames of a movie. The illusion of motion and change is created by the rapid succession of static frames. Each frame is a computed state of the universe, and what we perceive as the flow of time is simply the process of the universe calculating its next state, moment by moment. This revolutionary idea forces us to reconsider the very nature of reality. If time is emergent, then the past, present, and future might not be fundamentally distinct. The entire history of the universe could, in a sense, already be computed not as a predetermined path, but as a vast four-dimensional block where every moment exists equally, a concept known as the block universe in eternalism. From this perspective, the feeling of a moving now is a subjective experience generated by our brains as they process information sequentially within this frozen structure. We are like a reader moving through a book. The entire story is already written on the pages, but we experience it word by word. This doesn't make our experience any less real, but it suggests that the flow of time is a property of our interaction with the universe's computation, not a property of the computation itself. This profound connection between time and computation shows that time is not just a resource the universe uses. It is a product of the universe's relentless, step-by-step process of calculating its own existence. And this brings us to the most powerful and cutting-edge metaphor for this entire process: the possibility that the universe is not just like a computer, but that it literally is a quantum computer. This concept of time as an emergent property of a deeper computation brings us to a breathtaking and powerful metaphor that unites everything we've explored: the idea that the universe isn't just like a computer, but that it literally is one, and not just any computer, but the most powerful kind conceivable, a vast cosmic-scale quantum computer. To understand this, we need to shift our perspective from the classical computers we use every day. A classical computer, like the one in your phone or laptop, operates on bits. Each bit is a tiny switch that can be in one of two states, a 0 or a 1. Every calculation, from displaying a cat video to simulating the weather, is ultimately a vast sequence of these binary switches flipping on and off according to a programmed algorithm. It's incredibly powerful, but it's also linear and local. It does one logical operation after another. Now, imagine a computer that operates on an entirely different principle. This is a quantum computer, and its basic unit of information isn't the bit, but the quantum bit or qubit. A qubit is a revolutionary thing. Thanks to the quantum phenomenon of superposition, a qubit doesn't have to be just a 0 or a 1. It can be both at the same time, in a blended state of infinite possibility. This isn't just a small tweak, it's a complete game changer. If you have two classical bits, they can represent one of four possible states: 0, 0, 0, 1, 1, 0, or 1, 1. But they can only be in one of those states at a time. Two qubits, however, can be in a superposition of all four states simultaneously. As you add more qubits, the processing power doesn't just increase, it explodes exponentially. 3 qubits can represent 8 states at once, 4 qubits can represent 16, and so on. A quantum computer with just 300 qubits could, in principle, be in more simultaneous states than there are atoms in the entire observable universe. This means a quantum computer can perform a staggering number of calculations in parallel, exploring a near-infinite landscape of possibilities all at the same time. If our universe is indeed such a quantum computer, then every fundamental particle, every electron, every photon, is not just a particle but an active qubit, a tiny information processing unit existing in a haze of multiple possibilities. The cosmos itself would be an unfathomably dense network of these qubits, constantly interacting and performing calculations on a scale beyond human comprehension. This is where the universe's true computational power is unleashed. It isn't performing one calculation at a time. It is performing an almost infinite number of calculations simultaneously across every point in space for every moment in time. The evolution of the universe from the Big Bang to the present day would be the result of this monumental quantum computation running its course. The formation of galaxies, the nuclear fusion in stars, and even the chemical reactions in a single cell would all be emergent outcomes of this underlying quantum processing. The laws of physics we've discovered would be the algorithms that this cosmic quantum computer is running. This mind-bending idea is given serious weight by physicists like Seth Lloyd of the Massachusetts Institute of Technology. Lloyd has actually attempted to estimate the raw computational capacity of the universe. He calculated that since the Big Bang, our universe has performed about 10 to the power of 120 elementary logical operations on about 10 to the power of 90 qubits, which is roughly the number of elementary particles in the observable universe. This isn't just a fun analogy, it's a quantitative physical model. In this view, the history of the universe is quite literally the history of a computation. What we perceive as the passage of time is the sequence of these logical operations. What we perceive as the forces of nature are the ways the qubits interact and influence each other's states. The universe isn't running a simulation, it is the computation. This model becomes even more powerful when we consider the strangest and most spooky feature of quantum mechanics, as Einstein called it, entanglement. Entanglement is a profound connection that can form between qubits. When two particles become entangled, they lose their individual identities and become part of a single, unified quantum system. Their properties are linked in such a way that measuring the state of one particle instantly determines the state of the other, no matter how far apart they are across a room or across the galaxy. This instant connection, which seems to violate the cosmic speed limit of light, is what allows for non-local computation. It's as if the universe's quantum computer has a secret, ultra-fast wiring system that connects its most distant components, allowing them to share information and coordinate their actions without any delay. This isn't magic, it's a fundamental feature of how information is processed at the quantum level. Entanglement is the mechanism that weaves the universe together into a single, coherent whole, ensuring that the separate computations happening in distant galaxies are all part of one unified process. It is the glue that binds the cosmic quantum computer into a single, integrated system, allowing it to compute the complex, correlated structures we see, from the symmetry of a snowflake to the large-scale patterns of the cosmic web. This incredible, interconnected view of reality as a single quantum computation naturally leads us to an even more astonishing possibility, that the three-dimensional reality we experience might be a projection, a hologram, generated from information stored on a distant, two-dimensional surface. But if the universe is indeed a quantum computer of unimaginable scale, a new and even more radical question emerges: where is all this information actually stored? We are used to thinking of reality as a three-dimensional volume, with events happening within its expanse. But what if that volume is not the primary reality? What if everything we see and experience is actually a projection, a hologram, generated from information encoded on a distant, two-dimensional surface? This is not science fiction. It is a serious theoretical idea known as the holographic principle, and it represents one of the most profound revolutions in our understanding of space, time, and information itself. The principle suggests a staggering possibility: the entire universe, in all its three-dimensional richness and complexity, might be like a movie screen image. The actors, the landscapes, the depth, it all appears real to us, but it is all generated from data encoded on the two-dimensional surface of the screen itself. In this cosmic analogy, the information needed to describe every particle, every force, and every event within a volume of space is not stored throughout that volume. Instead, it is painted bit by bit on the boundary that encloses it. The most compelling evidence for this astonishing idea comes from the most extreme information processors in the cosmos: black holes. The black hole information paradox we encountered earlier created a deep crisis in physics. How could a black hole destroy information, violating quantum mechanics, when it evaporates via Hawking radiation? The resolution, pioneered by physicists like Leonard Susskind and Gerard T. Hooft, was as elegant as it was bizarre. They realized that if you throw an object into a black hole, say, a book containing a vast amount of information, that information is not lost inside the singularity. Instead, it becomes encoded on the black hole's event horizon, the point of no return. The event horizon is a two-dimensional surface, but it somehow manages to store all the information about the three-dimensional objects that have fallen in. As the black hole evaporates, this information is slowly and faithfully released back out into the universe through the subtle correlations in the Hawking radiation it emits. The information is never truly destroyed. It is just translated from a three-dimensional form to a two-dimensional one and back again. This discovery led Susskind and others to a breathtaking generalization. If a two-dimensional surface can hold the information for a three-dimensional volume of space in the special case of a black hole, perhaps this is a universal law. Perhaps all regions of space, from the smallest cube to the entire observable universe, obey this same holographic rule. This transforms our view of reality in a fundamental way. The world we live in would not be the primary reality. The true, fundamental description of the universe would be written on a vast, remote, two-dimensional boundary that encloses everything. Our experience of living in a three-dimensional world with depth and volume would be a magnificent illusion, a projection that emerges from the complex processing of that lower dimensional data. In this view, the universe isn't just computing itself, it is projecting itself, The cosmic quantum computer's hard drive is not inside the simulation. It is the two-dimensional surface upon which the simulation is encoded. The laws of physics that we experience in 3 dimensions would be a direct consequence of how information is organized and processed on that distant, lower dimensional surface. This provides an incredibly powerful and elegant solution to the problem of how the universe stores the unimaginable amount of information required to specify the state of every particle. There is a fundamental limit derived from this principle to how much information can possibly be contained within any given region of space. It is not infinite. The universe, in its most basic form, might be a vast but finite array of information bits, and our rich, 3-dimensional reality is the incredible, dynamic computation that emerges when that information is read out and processed. This holographic view forces us to reconsider the very nature of existence. Are we and everything we see just shadows on a wall? Is matter itself an illusion, a secondary phenomenon that emerges from the interactions of information? The theories of Susskind and others push us toward this conclusion, suggesting that the solidity of the world is a kind of user interface for a deeper, informational reality that operates in fewer dimensions. It implies that the universe computes itself not from within, but from the edges, from a boundary we cannot see or access. This is a profound and humbling idea, but it also points toward a deep and hidden order within the cosmos. For a projection to be stable and coherent, not just random noise, it must operate according to strict, invariant rules. This inherent need for stability and order in the cosmic computation brings us to one of the most beautiful and powerful concepts in all of physics, the role of symmetry. If the holographic universe is a projection, a magnificent illusion computed from a 2-dimensional boundary, what are the rules that ensure this projection remains stable, coherent, and predictable? Why does reality not simply flicker and dissolve into chaotic nonsense? The answer lies in one of the most beautiful and powerful concepts in all of science, symmetry. Look around the natural world and you will see symmetry everywhere, in the radial perfection of a snowflake, the bilateral mirroring of a human face, or the spherical shape of a soap bubble. These are not just aesthetic accidents, they are profound clues to the deepest operational rules of the cosmos. In physics, symmetry has a very specific and powerful meaning. It refers to an invariance, a property of a system that remains unchanged or invariant under a specific transformation. It is the universe's way of saying, no matter how you look at me from this angle or that, this fundamental property will always hold true. These symmetries are not mere suggestions. They are the immutable, non-negotiable algorithms that provide the bedrock stability for the entire cosmic computation, ensuring that the laws of physics remain consistent everywhere and for all time. The most breathtaking revelation about these symmetries is that they are not just passive features of the world, they are actively generative. They give birth to the very laws that govern motion and change. This profound connection was unveiled in 1918 by the brilliant German mathematician Emmy Noether. Noether's theorem is a cornerstone of theoretical physics, and its elegance is staggering. In simple terms, it states that for every continuous symmetry in the laws of physics, there corresponds a conserved quantity, a property of a system that remains constant over time, no matter what interactions occur within it. It is a direct, one-to-one mapping between a beautiful abstract principle and a concrete, measurable reality. This theorem is the hidden bridge between the geometry of the universe and its dynamics, revealing that the most fundamental conservation laws are not separate rules but direct consequences of the universe's inherent symmetries. Let's make this tangible with a classic example. Imagine a physicist performing an experiment in her lab. She sets up her equipment, runs the test, and gets a result. Now imagine she picks up her entire lab, moves it to another city, and repeats the exact same experiment. She will get the exact same result. The laws of physics are invariant under translation in space. It doesn't matter where you are. This spatial symmetry, the fact that the universe is homogeneous, that it looks the same everywhere, is not just a nice feature. According to Noether's theorem, this specific symmetry directly implies the law of conservation of linear momentum. Momentum, the product of mass and velocity, must be conserved in any closed system. If you push against a wall while wearing roller skates, you fly backward because your momentum forward is balanced by the wall's momentum backward. The total momentum remains zero. This isn't just a rule, it is a necessary computed outcome of the universe's spatial symmetry. Now consider another transformation. Our physicist runs her experiment at 10 in the morning, gets a result, and then runs the identical experiment at 10 in the evening. She will get the same result. The laws of physics are invariant under translation in time. It doesn't matter when you do the experiment. This temporal symmetry, the fact that the laws themselves do not change from one moment to the next, is directly linked by Noether's theorem to one of the most fundamental laws of all, the conservation of energy. Energy cannot be created or destroyed. It can only change form from kinetic to potential, from chemical to thermal. The total energy in a closed system is always constant. This provides an incredible stability to the cosmic calculation. The universe can compute incredibly complex reactions, stars fusing hydrogen, plants photosynthesizing sunlight, cars burning gasoline, but the total energy bookkeeping must always balance. It is an immutable algorithm hardwired into the fabric of reality by the symmetry of time itself. Perhaps the most intuitive example is rotational symmetry. The outcome of a physical experiment does not depend on the direction you are facing. The laws of physics are the same whether you are looking north, south, east, or west. The universe is isotropic. This symmetry of rotation gives us the conservation of angular momentum. A spinning ice skater pulls her arms in and she spins faster. Her angular momentum, the product of her rotational inertia and her rotational velocity, must remain constant. This is why planets maintain their orbits and why a gyroscope resists being tipped over. These conserved quantities, energy, momentum, angular momentum, are the universe's ultimate invariants. They are the fixed points in the calculation, the unchanging parameters that ensure the computation of reality is stable, predictable, and coherent across the vastness of space and time. They act as global constraints, forcing the endless dance of particles to always balance its books, providing the consistent rules that allow complexity to emerge from chaos without the entire system flying apart. These symmetries are the deepest algorithms in the cosmic code, the foundational principles that allow the universe to compute itself into the magnificent, ordered structure we observe. And this very idea of a cosmic code of immutable algorithms naturally leads us to wonder if this computation is not just mathematical, but literally digital. But this elegant, continuous world of smooth curves and unbroken symmetries might itself be an illusion, a convenient approximation of a much stranger and more fundamental truth. What if, at its very core, the universe isn't smooth and continuous at all? What if it is digital? This is the radical proposition of digital physics, a theory that suggests reality is not analog but discrete, composed of a finite number of tiny, indivisible bits of information, like a cosmic grid of pixels or a colossal cellular automaton running the ultimate simulation. It's the idea that the universe doesn't just compute, it is a computation in the most literal, bit-by-bit sense imaginable. The seeds of this revolutionary idea were planted not by a physicist, but by a pioneering computer scientist. In the 1960s, Konrad Zuse, the German engineer who built the world's first programmable computer, began to wonder if the universe itself might be operating on similar principles. He proposed a theory he called Rechnender-Raum, or computing space. Zuse suggested that the entire cosmos could be thought of as a giant digital computer, a cellular automaton where the state of each discrete cell in space is determined by the states of its neighbors according to a fixed set of rules. In this view, the laws of physics aren't continuous equations. They are the software, the algorithm that this cosmic computer is executing. Every event, from the motion of a planet to the firing of a neuron, would be the output of this vast, distributed calculation. This idea was later taken up and championed with profound conviction by another visionary, Edward Fredkin. A professor at the Massachusetts Institute of Technology, Fredkin was a unique blend of computer scientist and philosopher. He became the most ardent proponent of what he called digital mechanics. Fredkin didn't just suggest the universe was like a computer, he argued it literally is one. He proposed that there exists a fundamental, immutable process, a kind of cosmic clock that ticks forward, updating the state of every bit of reality at each step. Time in this model is not a smooth flow but a sequence of discrete moments like the frames of a film, and space is not infinitely divisible, it is a fixed, finite grid. For Fredkin, this wasn't just a metaphor, it was the true nature of reality, and he believed that discovering this underlying digital code was the ultimate goal of physics. This pixelated perspective on reality finds its most compelling evidence in the bedrock of modern physics itself, the Planck scale. Named after the physicist Max Planck, the Planck length and Planck time are the smallest possible units of meaningful measurement. The Planck length is an almost unimaginably tiny distance, about 1.6 times 10 to the power of negative 35 meters. To put that in perspective, if you enlarged a single atom to the size of the observable universe, a Planck length would be roughly the height of an average tree. Similarly, the Planck time is the time it takes for light to travel that minuscule distance, about 10 to the power of negative 43 seconds. These aren't just small numbers. Many physicists believe they represent a fundamental limit. You cannot measure anything smaller than a Planck length. The very concepts of length and duration may break down beyond this scale. This provides a tantalizing hint that space and time might not be smooth and continuous, as Einstein's theories describe, but are instead granular and discrete, composed of individual pixels of spacetime. The smooth, curved geometry of general relativity would then be an emergent property, a large-scale average of these tiny, digital building blocks, much like a digital photograph appears smooth and continuous from a distance but reveals its pixelated nature when you zoom in. This digital view of the cosmos presents a direct and profound challenge to the continuous models that have dominated physics for centuries. The majestic equations of Newton and Einstein, which describe gravity and motion as smooth curves in a continuous fabric, have been spectacularly successful. But digital physics asks us to consider that these equations might be approximations, incredibly accurate and useful approximations, to be sure, but approximations nonetheless. They would be like the equations of fluid dynamics, which perfectly describe the behavior of water in waves and currents without needing to account for every single H2O molecule. The true, fundamental laws would be the digital algorithm that governs the interactions of the universe's primitive bits. This shift in perspective would be a scientific revolution on par with the discovery of quantum mechanics, forcing us to rewrite our most basic understanding of reality from the ground up. It suggests that the universe is not only computed, but is fundamentally computational in its very substance. And if our universe is one specific computation running on a finite grid, it naturally compels us to ask a staggering question: could there be other programs running elsewhere? This digital, pixelated view of our own universe as a specific computation running on a finite grid of spacetime inevitably opens the door to a possibility of staggering proportions. If our reality is one particular program, one specific set of algorithmic rules being executed, then what is stopping other programs from running elsewhere? This line of thinking propels us beyond the confines of a single cosmos and into the vast, almost unimaginable landscape of the multiverse. Here, the concept of cosmic computation expands exponentially, suggesting that our universe might be just one instance in a near-infinite array of parallel computations, each running with its own unique set of rules, its own version of physics, and its own potential for life or something utterly beyond our comprehension. The most scientifically robust pathway to this multiverse idea comes not from quantum theory, but from cosmology itself, specifically from the theory of cosmic inflation. This theory proposes that in the first fleeting fraction of a second after the Big Bang, the fabric of spacetime underwent a period of hyper-accelerated expansion, stretching by an enormous factor in an incredibly short time. This process elegantly explains many features of our universe, like its overall flatness and uniform temperature. But many versions of inflationary theory carry a fascinating implication. This expansion may not have been a one-time event that started and stopped everywhere at once. Instead, it might be an eternal process. In this eternal inflation scenario, the repulsive energy driving the expansion can decay in some regions like ours, creating a stable, bubble universe with its own local laws of physics, while the inflationary process continues unabated in the surrounding space. New bubbles are constantly nucleating in this eternally inflating background, each one a separate pocket universe with its own Big Bang. It's like a vast, boiling pot of water, where bubbles of steam continuously form and rise to the surface. Each of these bubble universes could have its own unique set of fundamental constants. In one, the strength of the nuclear forces might be slightly stronger, preventing hydrogen from ever forming. In another, the cosmological constant might be so large that the universe tears itself apart instantly. Our universe, with its seemingly fine-tuned constants that allow for galaxies, stars, and life, would then be just one particularly hospitable bubble in a frothing, infinite cosmic sea, a single, successful computational instance that found a stable and complex solution. This cosmological picture finds a powerful and deeply computational parallel in the many worlds interpretation of quantum mechanics, proposed by Hugh Everett III. We already saw how the quantum world computes all possibilities simultaneously. The standard Copenhagen interpretation says that this haze of potentialities collapses into a single reality upon observation. But the many worlds interpretation offers a radically different and breathtakingly elegant solution. There is no collapse. Instead, every single possible outcome encoded in the quantum wave function actually happens. The universe's quantum computer doesn't choose one path. It computes all paths, and each one branches off into its own separate, equally real world. At every quantum junction, every particle decay, every photon reflection, the entire universe effectively splits into multiple branches, each one recording a different outcome. In one branch, the radioactive atom decays at this precise moment. In another branch right beside it, it does not. In one branch, you turned left on your way to work. In another, you turned right and had a completely different day. There is no single timeline, but a constantly proliferating tree of possibilities, with every branch representing a parallel computation of reality. This isn't science fiction. it is a serious and for some physicists a preferred solution to the quantum measurement problem. It frames the multiverse not as a collection of distant, disconnected bubbles, but as an ever-diverging set of parallel worlds, all existing in a vast, higher-dimensional quantum state, all being computed concurrently. Whether we envision a landscape of inflationary bubbles or an endlessly branching quantum tree, the computational implications are profound. The cosmos becomes a multiscalar computer of unimaginable capacity. Each universe, each branch, is a separate computational instance running its own unique program, defined by its local physical laws and constants. Some of these programs would be incredibly short and simple, universes that immediately collapse or dissipate. Others might be stable but barren, vast empty expanses where nothing interesting ever happens. And a tiny, perhaps infinite subset would be universes like ours, with the right algorithmic parameters to compute galaxies, chemistry, and conscious beings who can wonder about it all. This framework transforms the philosophical puzzle of fine-tuning. The question is no longer, why are our constants so perfectly set for life, but becomes, in the vast array of all possible computational outputs, we naturally find ourselves within one of the subsets that can support observers. We are not a lucky accident. We are an inevitable statistical outcome in a sufficiently vast multiverse of computations. This expansion of perspective to a multiscalar level is both humbling and empowering. It suggests that the processes we see at work in our universe, the emergence of complexity from simple rules, the relentless drive of entropy, the quantum computation of possibilities, are not unique to our local reality. They may be universal principles of existence playing out in countless variations across the multiverse. The cosmic computer is not running one program, it is running them all, exploring the entire logical space of possible universes. And as we peer into the depths of our own universe, trying to understand its most fundamental algorithms, we are confronted by two of its most mysterious components, whose nature might hold the key to the entire computational structure: dark matter and dark energy. Yet for all their profound influence, these two hidden components remain utterly elusive. We cannot see dark matter because it does not interact with light. It neither emits, absorbs, nor reflects photons. We cannot contain dark energy because it appears to be a property of empty space itself, a smooth, uniform energy density that permeates the entire cosmos. Their existence is inferred solely through their gravitational signature, like deducing the presence of a hidden object by watching how visible things move around it. They are the ultimate hidden variables in the universe's computation, parameters in the cosmic algorithm that we know must be there because of the output we see, but whose fundamental nature and purpose remain one of science's greatest enigmas. A powerful analogy for this can be found in computer programming, particularly in the concept of hidden variables or global constants. Imagine a sophisticated video game with an incredibly realistic physics engine. A player within the game might meticulously study the behavior of objects, how they fall, how they collide, how light reflects off them. Through observation, they could reverse engineer many of the game's laws. They might deduce the value of the virtual gravitational constant or the coefficient of friction. But what if the game's programmer had also included a global variable, a hidden parameter that subtly influences the rate at which the entire game world is expanding? The players, confined within their reality, would see all the galaxies of their game universe moving apart at an accelerating rate. They would be forced to conclude the existence of a mysterious, unseen energy causing this effect, even though they could never directly access or measure the line of code that defines it. Dark matter and dark energy appear to be the universe's own hidden global variables, deeply embedded in its source code, shaping the grand outcome of the computation in ways we can detect but not yet fully comprehend. This mystery places us at a thrilling and frustrating frontier of knowledge, the standard model of cosmology, which beautifully describes the evolution of the universe from a hot, dense state to the vast cosmic web we see today, is often called the lambda cold dark matter model. In this title, lambda represents the cosmological constant, our best current mathematical description for dark energy, and cold dark matter refers to the prevailing theory that dark matter is made of slow-moving, exotic particles. This model is a spectacularly successful computational framework. It allows us to run simulations of the entire universe that match our observations with stunning accuracy. But it is a model built upon profound unknowns. It is as if we have a perfect user manual for a machine, detailing exactly what every button does and how all the gears interact, but we have absolutely no idea what the machine's most critical parts are actually made of. We can use the model to predict the universe's behavior, but we still lack the fundamental understanding of what constitutes the vast majority of it. The global scientific effort to decode these hidden variables is one of the most ambitious detective stories ever undertaken. To identify dark matter, physicists have built incredibly sensitive detectors deep underground in abandoned mines and tunnels, shielding them from cosmic rays. These experiments, with names like LUX Zeppelin and Xeno NNT, are waiting for the once-in-a-lifetime event where a hypothetical dark matter particle, known as a WIMP, a weakly interacting massive particle, might bump into the nucleus of a xenon atom and create a tiny, detectable signal. In space, the Fermi Gamma Ray Space Telescope scans the heavens, hoping to see indirect evidence of dark matter particles annihilating each other and producing gamma rays. Meanwhile, to understand dark energy, projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory are meticulously mapping the positions and distances of billions of galaxies, measuring the history of the universe's expansion with exquisite precision to determine if the strength of dark energy has changed over time. The goal is to see if our lambda is truly a constant, as Einstein proposed, or something more dynamic and strange. The enduring enigma of dark matter and dark energy serves as a powerful and humbling reminder. Our journey to understand the universe as a self-calculating system is far from complete. We have uncovered profound algorithms in the laws of physics, from quantum mechanics to general relativity, and we have seen how complexity and consciousness can emerge from their relentless execution. But these two dark components show us that our map of reality is still missing its largest territories. They are the glaring blanks on the cosmic schematic, the unknown commands in the source code that dictate the overall structure and fate of everything. They represent the current limit of our comprehension, a frontier where the known laws of physics seem to whisper that a deeper, more complete theory must be waiting to be discovered. This isn't a failure of science, it is its greatest excitement. It means the cosmic computation is even more mysterious, more sophisticated, and more magnificent than we have yet been able to imagine. This quest to measure the universe's complexity through its most concise description leads us directly to a fascinating and powerful branch of mathematics known as algorithmic information theory. Developed independently by Ray Solomonoff, Andrei Kolmogorov, and Gregory Chaitin in the 1960s, this theory offers a radically objective way to define what we even mean by complexity and randomness. The core idea is beautifully simple yet profound. The complexity of an object, whether it's a number, an image, or a physical structure, can be measured by the length of the shortest computer program required to generate or describe it. This is often called its Kolmogorov complexity. Think of it as the ultimate test of compressibility. A highly ordered, simple object has very low complexity because it can be described by a very short program. The sequence of digits for the number pi, for instance, goes on forever without repeating, appearing utterly random. But it actually has a very low Kolmogorov complexity because a relatively simple algorithm can generate its endless digits. The program is short, the output is infinite and seemingly patternless. Now apply this breathtakingly elegant idea to the grandest object of all, the universe itself. We can look out at the night sky with all its swirling galaxies, nebulae, and cosmic webs, and be overwhelmed by its apparent complexity. But is it truly complex, or is it just complicated? Algorithmic information theory gives us the tools to ask a staggering question. What is the minimal amount of information, the shortest algorithm, required to compute our entire reality? What is the Kolmogorov complexity of the cosmos? Is the universe something that can be described by a beautifully compact set of equations, a short program that fits on a t-shirt, or is its description irreducibly long, making it fundamentally random and incompressible? The hope of fundamental physics has always been the former, that beneath the staggering variety and detail of the observable world lies a short, elegant, and simple set of laws. The entire enterprise of theoretical physics is a search for this short program. Gregory Chaitin's work, however, introduces a fascinating and almost philosophical hurdle to this search. He discovered that for any given mathematical system, there are numbers whose complexity is so high that they are algorithmically random. Their shortest description is essentially just to write them out in full. More profoundly, he proved that there is no systematic procedure, no ultimate algorithm, that can determine the Kolmogorov complexity of an arbitrary object. This is known as the incomputability of complexity. It's a result that carries a deep, almost existential weight for our cosmic inquiry. It suggests that while the universe may indeed be running on a program, we might never be able to conclusively prove that we have found the shortest, most fundamental version of that program. There might always be the possibility of an even shorter, more elegant set of laws waiting to be discovered, or it might be that the universe is, at its heart, algorithmically random. We can see this tension between simple rules and complex output play out vividly in the natural world all around us. Consider the coastline of a country like Norway, with its countless fjords, inlets, and rocky outcrops. From a satellite, its outline appears fantastically complex and irregular, a jagged mess that seems to defy simple description. If you tried to describe its exact perimeter by listing every single twist and turn at the atomic level, the description would be impossibly long. Its Kolmogorov complexity, if measured in this way, would be astronomically high, but we know that this complexity isn't truly random. It emerges from a surprisingly simple set of iterative processes, the relentless action of glaciers carving through rock, the constant pounding of waves eroding the shore, the uplift of tectonic plates. These processes often produce fractal patterns, which are geometric shapes that look similar at different scales. A tiny piece of the coastline looks roughly like a larger piece, which looks like the entire coastline. And fractals have a wonderfully low Kolmogorov complexity. They can be generated by very short, recursive algorithms. The famous Mandelbrot set, perhaps the most complex and beautiful image in all of mathematics, is produced by a single, simple equation iterated over and over. Its infinite detail is computed from a program that is just a few lines long. This is the magnificent paradox at the heart of a self-computing universe. The cosmos generates an explosion of apparent complexity and detail from what might be a remarkably compact and simple set of initial conditions and laws. The universe seems to possess what we might call high emergent complexity but potentially low fundamental complexity. Its endless richness and novelty may not be proof of a long, complicated program, but rather a testament to the power of a short, elegant program set running for billions of years. The cosmic computation is not random. It is the intricate and breathtaking output of a process that is, at its source, simple and compressible. This beautiful interplay between concise algorithms and their infinitely detailed outputs suggests that the universe is the ultimate example of getting more out of less, a cosmic magic trick where simplicity begets unending complexity. And this very process of a system generating complexity from its own simple rules inevitably leads to systems that can loop back and act upon themselves, a phenomenon that introduces a whole new layer of profundity to the cosmic calculation. This concept of a universe generating infinite complexity from finite rules leads us to one of the most fascinating and mind-twisting features of any computational system: the ability to fold back upon itself. We are now entering the realm of self-reference and recursion, where the cosmic computation doesn't just run in a straight line. It creates loops that feed their own outputs back in as new inputs. This isn't an abstract curiosity. It's a fundamental mechanism that shapes everything from the global climate to the inner workings of your own mind. And it may even place ultimate limits on what the universe can ever know about itself. We can see these recursive loops operating all around us. Consider Earth's climate system, a magnificent and complex dance of air, water, and energy. It's a vast planetary-scale feedback system. Here's a simple example. As global temperatures rise, polar ice caps melt. Ice is brilliant at reflecting sunlight back into space, but open ocean water is dark and absorbs that heat. So, less ice means less sunlight is reflected, which means more heat is absorbed by the planet, which leads to even higher temperatures and even more ice melt. This is a positive feedback loop, a self-reinforcing cycle where the output of the process amplifies the process itself. But there are also negative feedback loops that stabilize the system. For instance, warmer temperatures can lead to more water vapor evaporating from the oceans, which can form more clouds. Some clouds reflect sunlight, which can have a cooling effect, counteracting the initial warming. The entire climate is a symphony of these competing, recursive loops, each one a calculation where the result directly influences the next round of computation. The system is quite literally computing its own future state based on its past and present states, with no external program required. This recursive computation becomes even more intimate when we look inward at the neural networks inside our brains. Your perception of the world is not a passive reception of data. It is an active, recursive construction. Your brain is constantly generating predictions about what you are about to see, hear, and feel. These predictions are models built from your past experiences, your prior computations. Then, sensory information from the world comes in and is compared against this prediction. The difference between the prediction and the actual input generates a prediction error. This error signal is then fed back up the neural hierarchy to update and refine the model for next time. You're not just seeing a chair, your brain is predicting chair, and the sensory confirmation simply tells it the prediction was mostly correct, fine-tuning the internal model ever so slightly. This is recursion in its purest form. The brain's model of the world is both the source of the prediction and the thing that is updated by the result. Your consciousness itself can be seen as this ongoing, recursive loop of prediction and correction, a universe modeling process that is continuously computing and recomputing itself. But what happens when this powerful concept of self-reference is applied not just to physical systems, but to the very logical foundations of reality itself? This question leads us to one of the most profound discoveries in all of mathematics, Gödel's incompleteness theorems. In the 1930s, the logician Kurt Gödel delivered a stunning blow to the dream of a perfectly complete and consistent mathematical system. He proved, in essence, that any sufficiently powerful formal system, one that is complex enough to describe basic arithmetic, is fundamentally incomplete. This means there will always be true statements within the system that cannot be proven to be true using only the rules and axioms of that same system. Furthermore, he showed that such a system cannot demonstrate its own consistency from within itself. You cannot use the rules of a system to prove that those very rules will never lead to a contradiction. Now apply this earth-shattering idea to our self-computing universe. If the cosmos is indeed a computational system operating according to a fixed set of mathematical laws, a formal system of immense power, then Gödel's theorems might apply to it directly. This suggests a staggering and humbling possibility. There could be fundamental limits to what the universe can ever compute about itself. There might be truths about reality, facts about its own existence and structure, that are forever beyond the reach of any calculation performed within the universe. The cosmic computer may be incapable of generating a complete and consistent theory of everything that explains its own origins and logic from the inside. It would be like a book trying to contain its own author, or a computer program trying to output its own source code in its entirety. A logical paradox that simply cannot be resolved from within the framework. The universe might be able to compute galaxies, stars, and conscious beings, but it may forever be unable to answer the most deep and meaningful questions about why it has the rules it does and where those rules ultimately came from. This isn't a failure of science, it is a fundamental feature of any self-referential system. And it suggests that the ultimate nature of reality might contain an inherent, unbridgeable mystery that no amount of processing power can ever dissolve. This intimate link between information erasure and energy dissipation leads us to a profound and universal characteristic of the cosmic computation, its inherent irreversibility. Most of the computations that shape our reality, from the firing of a neuron to the fusion of atoms in a star, are one-way streets. They cannot be simply run in reverse to return to their starting point. This isn't a limitation of our technology. It is a fundamental principle woven into the fabric of physics, and it mirrors perfectly the most famous one-way street in the entire cosmos: the relentless, irreversible increase of entropy. The universe's computation and its journey toward disorder are two sides of the same coin, a deep connection that gives direction to time itself and dictates the very fate of everything. We can see this computational irreversibility in the simplest of actions. Imagine deleting a file on your computer. You highlight the icon, press the delete key, and it vanishes from your desktop. But what has actually happened? The information that made up that file, the specific pattern of ones and zeros stored on your hard drive, hasn't been instantly obliterated. To truly erase it, to reset those magnetic domains to a standard, known state like all zeros, the drive must physically overwrite the old data. This act of overwriting, of forcing a disordered, random pattern into a specific, ordered state, requires energy. That energy is dissipated as heat, a tiny puff of warmth radiating from your laptop. This is Landauer's principle in action, demonstrating that the logical act of irreversible information processing is inextricably bound to a physical, thermodynamic cost. Now scale this idea up from a single bit to the entire universe. Every time a star converts hydrogen into helium, it is processing information about nuclear states. Every time a plant performs photosynthesis, it is processing information about light photons. And with each of these countless computations, information is effectively erased and heat is released, contributing imperceptibly but inexorably to the universe's total entropy. The cosmic computer is constantly warming up as it runs, and there is no cooling fan for the universe. This irreversible nature of information processing is the hidden engine behind the arrow of time. Why do we remember the past but not the future? Why does an egg easily scramble but never spontaneously unscramble itself? The answer lies in this link between computation and entropy. The universe began in a state of incredibly low entropy, a highly specific, ordered configuration after the Big Bang. As it computes its way forward, moment by moment, it explores new states. But because most computational operations are irreversible, the system cannot easily backtrack. It can only move forward into states of higher probability, states with more possible configurations, which is the very definition of higher entropy. The act of computation itself creates a record of the past in the present. The specific arrangement of neurons in your brain that constitutes a memory is a physical record of a past computation. The light from a distant star that reaches our telescopes is a record of nuclear computations that happened millions of years ago. The past is fixed because it has been computed and recorded in the present structure of the universe. The future, by contrast, is a haze of possibilities because it has not yet been computed. The irreversible processing of information is what carves the unique and consistent direction out of time's raw potential, giving us a past that is fixed and a future that is open. This has a breathtaking implication for the grand story of cosmic evolution. The universe's journey from a smooth, hot soup of particles to the complex tapestry of galaxies, stars, and planets we see today is not just a story of matter cooling and clumping together. It is a story of information processing and the inevitable increase in disorder that it produces. The formation of a single, ordered structure like a crystal or a planet is a local decrease in entropy, but it is always paid for by a larger, global increase elsewhere. A star, for instance, is a magnificent engine of order, forging heavy elements in its core. But to do this, it must burn its nuclear fuel, a process that releases a colossal amount of heat and radiation into the cold void of space, dramatically increasing the universe's overall entropy. The emergence of life is the ultimate local rebellion against disorder, creating islands of incredible complexity and information. But even life is powered by this same entropic trade. We consume energy from the sun or from food, processes that are wildly irreversible and that increase the total disorder of the universe in order to maintain our own exquisite internal order. The cosmic computation is not free. It is funded by a thermodynamic loan that must be repaid with interest in the form of dissipated heat. The entire evolution of the cosmos, from the first stars to the first cells, is driven by this inexorable one-way flow. But if the universe's computation is so deeply tied to its fundamental laws and constants, a truly radical question emerges. Are those laws themselves truly set in stone? We've been exploring a cosmos that calculates its own state using a fixed rulebook. But what if the rulebook itself is not a timeless, divine scripture, but something that can be edited, revised, and even evolved over time? This idea pushes the boundaries of physics into profoundly speculative territory, suggesting that the universe might not just be computing within its laws, but could actually be computing the laws themselves in a grand, meta-level process of self-optimization. This breathtaking concept finds one of its most compelling advocates in theoretical physicist Lee Smolin. In his theory of cosmological natural selection, Smolin makes a staggering proposal. Our universe might be the product of a Darwinian evolutionary process that operates on a cosmic scale. The theory starts with the formation of black holes, In our universe, a black hole's immense gravitational crush is thought to create a singularity, a point where the known laws of physics break down. Smollin suggests that rather than being a dead end, this singularity could be a gateway, a point where the space-time of our universe pinches off and gives birth to an entirely new, baby universe in a Big Bang-like event. This new universe would not be a perfect clone of its parent. Crucially, the fundamental constants and laws that govern it could be slightly different, a random mutation in the cosmic genetic code. Perhaps in this new universe, the strength of gravity is a fraction weaker, or the mass of the electron is a tiny bit heavier. This is where the natural selection part comes in. The fitness of a universe in Smollin's model is measured by its ability to produce black holes. Black holes are the reproductive mechanism. They are how a universe has offspring. Therefore, universes that have physical laws tuned to maximize black hole production will, by definition, create more baby universes. Over countless generations, this would lead to a predominance of universes with laws that are exceptionally good at making black holes. And here's the fascinating part: the same physical parameters that favor prolific black hole formation, things like the precise values of the cosmological constant and the strength of nuclear forces, also seem to be the very same parameters that allow for the existence of long-lived stars, stable planets, and ultimately, life. So, in this view, we don't live in a universe fine-tuned for life by a designer. We live in a universe fine-tuned for making black holes, and the conditions for life are a fortunate byproduct. It's a cosmic example of a selection pressure favoring fecundity, and we are simply along for the ride in a universe that is very, very good at replicating itself. This idea of a self-optimizing cosmos is powerfully echoed in the world of computer science through genetic algorithms. These are search-based optimization techniques inspired by natural selection. You start with a population of potential solutions to a problem, each encoded as a digital chromosome. You then test these solutions against a fitness function, a goal you want to achieve, like designing the most efficient wing shape or solving a complex equation. The solutions that perform best are selected to reproduce. Their digital chromosomes are combined crossover and randomly altered mutation to create a new generation of solutions. This new generation is then tested again, and the cycle repeats. Over many generations, the population evolves toward an optimal solution. Now, transpose this idea to Smollin's cosmology. The problem is the stability and longevity needed to form black holes. Each universe is a potential solution, with its set of physical constants acting as its chromosome. The multiverse is the population, black hole production is the fitness function, and the endless cycle of universe birth through singularities is the reproduction mechanism. The cosmos becomes a vast, ongoing genetic algorithm, meta-computing its own fundamental parameters to find the most successful configurations. This perspective completely inverts our traditional understanding. The laws of physics are no longer the unchanging foundation upon which the universe runs. They become the output of a deeper, more fundamental process. The universe is not just calculating within a framework, it is calculating the framework itself. This is a meta-computation of the highest order, an optimization loop written into the very fabric of existence. It suggests a reality that is not static but dynamic and evolutionary all the way down to its deepest principles. The seemingly arbitrary, fine-tuned numbers we measure might not be lucky accidents, but the hard-earned results of billions of years of cosmic trial and error, a testament to a process that has learned how to build a stable and productive universe. This idea that the universe can generate and test its own rules brings us to the most extreme environments where the nature of information itself is put to the ultimate test. But if the universe can indeed compute and even evolve its own fundamental laws, then we must now turn our attention to the most extreme environments where those laws are pushed to their absolute breaking point, where the very nature of information and computation faces its ultimate test. We are talking about black holes. These are not merely cosmic vacuums or destructive monsters. In the context of our computational universe, they are the most extreme information processors imaginable, natural supercomputers that operate under conditions so severe they challenge our most basic understanding of reality itself. A black hole is a region of space-time where gravity has won a total victory. Matter has been compressed to an infinitely dense point called a singularity, and the gravitational pull is so intense that not even light can escape from a boundary surrounding it known as the event horizon. From the outside, a black hole appears remarkably simple. It can be completely described by just three properties: its mass, its electric charge, and its spin. This simplicity presents a profound puzzle. Imagine you have a vast, complex library filled with millions of unique books, each containing immense amounts of information. Now you throw that entire library into a black hole. According to the classical view of black holes developed from Einstein's general relativity, all that information, the specific arrangement of every letter on every page in every book, is seemingly lost forever, crushed into the singularity. The black hole that remains is identical to one that formed from the collapse of a featureless cloud of hydrogen gas. It has the same mass, same charge, same spin. This is the heart of the black hole information paradox. The paradox emerges from a devastating clash between the two great pillars of modern physics, general relativity and quantum mechanics. Quantum mechanics is built on a foundational principle: information cannot be created or destroyed. It can be scrambled, transformed, and transferred, but it must be conserved. The universe, from a quantum perspective, is a fundamentally reversible computation. If you could somehow reverse all the motions of every particle involved in a process, you should be able to recover the original information. But general relativity, in the context of a black hole, seems to violate this sacred rule with impunity. This conflict reached its peak in a famous scientific bet. For decades, Stephen Hawking argued that the information swallowed by a black hole was indeed lost forever. He showed that black holes are not completely black. Due to quantum effects near the event horizon, they slowly emit radiation, now famously known as Hawking radiation. This radiation, he argued, is entirely random and thermal. It carries no information about what fell in. As the black hole radiates, it gradually loses mass and eventually evaporates completely, leaving behind nothing but this random thermal radiation. The original information from the library and every star and planet that ever fell in would be irrevocably erased from the universe. This suggestion that information could be destroyed was so troubling that it prompted physicist John Preskill to bet against Hawking. Chinese letter, Chinese letter, Chinese letter, Chinese letter must be preserved somehow. The potential resolution to this paradox forces us to reconsider the very nature of the event horizon. One radical idea that emerged is the concept of the firewall. If information is to be preserved and eventually returned via Hawking radiation, the mechanism might be incredibly violent. The proposal suggests that the event horizon might not be the smooth, uneventful space that general relativity describes. Instead, it could be a searing wall of high-energy particles, a firewall that would instantly incinerate anything crossing it. This would solve the information problem by effectively encoding the information of the infalling object onto the outgoing radiation at the moment of destruction. But this solution comes with a huge cost. It violates the core principle of general relativity, which states that an astronaut falling through the event horizon should not experience any special local effects. They should be peacefully and blissfully unaware of their point of no return until tidal forces eventually pull them apart. The firewall idea trades one paradox for another, highlighting the deep incompatibility between our current theories. The most promising and widely accepted resolution today draws us back to the holographic principle. The key insight is that all the information that falls into a black hole is not lost inside the singularity. Instead, it is meticulously encoded on the surface area of the event horizon itself. The three-dimensional information of the library is compressed into a two-dimensional holographic representation on the black hole's boundary. This is not a metaphor. The mathematics suggests that every bit of information that falls in increases the surface area of the event horizon by a tiny, precise amount, in units of the Planck area. Then, as the black hole emits Hawking radiation, this process is not random. The radiation particles are subtly entangled with the information on the horizon. As the black hole evaporates, this information is slowly and faithfully decoded back into the universe. The information was never truly lost. It was just translated into a different language and stored on a two-dimensional surface before being transmitted back out. This holographic resolution is a stunning victory for the principle of information conservation and provides incredible support for the idea that the universe is, at its most fundamental level, an information processing system. Stephen Hawking himself eventually came to accept this view, conceding his famous bet to Preskill. The journey to this understanding shows us the absolute limits of our current computational models of the universe. Black holes are the ultimate natural laboratories, forcing us to develop new physics that must unite gravity and quantum mechanics into a theory of quantum gravity. They are the universe's most extreme processors, testing information and computation under conditions we can barely imagine. They challenge us to think not in terms of particles and forces alone, but in terms of bits, entropy, and information capacity. The way they manage information hints at a deeper holographic reality, suggesting that our three-dimensional experience is a projection computed from a two-dimensional source. This profound struggle to understand what happens to information in a black hole is not just an abstract puzzle. It is a crucial battle in our war to understand the fundamental rules of the cosmic computation. Rules that must hold true even in the most violent and unforgiving environments nature can create. This profound puzzle of why our universe seems so perfectly tailored for our existence brings us directly to one of the most debated and fascinating ideas in modern cosmology, the anthropic principle. At its heart, this principle is a statement about observation. It suggests that the fundamental constants of the universe appear finely tuned for life for one very simple, almost tautological reason. If they weren't, we wouldn't be here to notice. We are, in a sense, selecting for this particular universe simply by virtue of being conscious observers within it. It's like a lottery winner marveling at the astronomical odds of their victory, while forgetting that someone had to win, and their existence as the winner is what allows them to marvel in the first place. The universe isn't fine-tuned for life in general. It is fine-tuned for the specific kind of life that can arise within its particular set of rules, and we are a product of that specific tuning. This concept moves from a philosophical curiosity to a powerful scientific tool when we place it within the framework of a computational multiverse. If our reality is just one of a vast, perhaps infinite, number of parallel computations, each running with a slightly different set of initial parameters and physical constants, then the anthropic principle becomes a powerful form of selection bias. We should not be surprised to find ourselves in a universe that permits our existence, even if such a universe is incredibly rare. Imagine a vast cosmic casino with an infinite number of slot machines, each representing a different universe with its own unique settings. Most of these machines are losers. They're universes that flash and die instantly, or ones that expand into cold, empty voids, or ones where matter is too unstable to form even a single atom. But a tiny, tiny fraction of these machines will, by pure chance, have the right combination of symbols to hit the jackpot. A universe stable and complex enough to give rise to stars, planets, and ultimately conscious observers. We, as the observers, inevitably find ourselves standing in front of one of those jackpot machines. The odds of any particular universe being life-permitting might be infinitesimally small, but in a sufficiently large multiverse, the probability that some universe will hit the jackpot becomes a near certainty. The evidence for this apparent fine-tuning is startlingly precise. Consider the production of carbon, the fundamental building block of life as we know it. Inside stars, carbon is forged in a two-step process. First, two helium nuclei fuse to form a very unstable isotope of beryllium. Normally, this beryllium would fall apart almost instantly, far too quickly for a third helium nucleus to collide with it to form carbon. But it doesn't. There is a specific, exquisitely tuned resonance in the nucleus of a carbon atom that matches the energy of the incoming beryllium and helium nuclei almost perfectly. This resonance acts like a catcher's mitt, dramatically increasing the probability of a successful fusion event and allowing carbon to accumulate in the stellar cores. The renowned physicist Fred Hoyle famously predicted this resonance based on the logical necessity for carbon-based life to exist, and experiments later confirmed his prediction with stunning accuracy. If the strong nuclear force were even slightly stronger or weaker, this resonance would not exist, and the universe would be devoid of carbon, oxygen, and the breathtaking chemistry of life. This isn't an isolated example. The strength of gravity, the mass of the proton, the value of the cosmological constant, all seem to reside in a very narrow, Goldilocks zone that allows for complexity. This breathtaking precision inevitably leads to a monumental question. Does this fine-tuning imply the existence of a cosmic programmer, a divine architect who deliberately set the dials to these life-giving values? Or is it simply the result of a magnificent, random roll of the dice in a multiverse of unimaginable size? The computational perspective offers a powerful third option that sits between these two extremes. It suggests that the fine-tuning may not be for life per se, but for complexity. A universe that can compute its own existence over billions of years requires a very specific set of algorithmic parameters to avoid immediately fizzling out or collapsing. The constants need to allow for the formation of stable structures, atoms, stars, galaxies that can persist long enough for the long, slow computation of emergent complexity to occur. In this view, life is not the goal of the computation, but one of its most astonishing and complex possible outputs. The universe is not fine-tuned for us. We are a natural, emergent consequence of a universe that is fine-tuned for stability, longevity, and complex computation. The programmer isn't an external entity. The program itself contains the necessary rules to generate observers from within. This elegantly reframes the debate, moving it from a question of purpose to a question of process and possibility within a vast computational landscape. This journey through the multiverse and the anthropic principle inevitably leads us to one of the most provocative and widely debated ideas of our time, a hypothesis that takes the concept of a computed universe to its ultimate, and for some, terrifying conclusion. What if our entire reality, with all its beauty, pain, and complexity, is not a fundamental existence but a sophisticated simulation, a kind of ultra-advanced video game running on the hardware of some higher dimensional civilization. This is the simulation hypothesis, an idea that has leapt from the pages of academic philosophy into the mainstream, fueled by figures like Oxford's Nick Bostrom and even entertained by prominent technologists. Bostrom's seminal argument doesn't claim we are definitely in a simulation, but rather presents a striking logical trilemma. He suggests that at least one of three propositions must be true. First, that almost all civilizations at our level of technological development go extinct before achieving post-human capabilities. Second, that even if they survive, almost none are interested in running detailed ancestor simulations. Or third, that we are almost certainly living in a simulation right now. The argument is based on a simple extrapolation of technological trends. If a civilization does not destroy itself and continues to advance, it would presumably develop computational power far beyond our own. The ability to simulate conscious minds or even entire worlds might become a trivial exercise for such a society, perhaps for historical research or entertainment. If even a small fraction of these civilizations run even a small number of such simulations, the number of simulated minds would quickly and vastly outnumber the number of biological, base reality minds. Therefore, statistically, any given conscious being, like you or me, is far more likely to be one of the simulated ones than an original. The scientific arguments for this idea often draw compelling parallels to our own technological creations. Look at the staggering progress in video game graphics and physics engines over just the past few decades. We have moved from simple, blocky worlds to vast, open-world environments with realistic lighting, weather systems, and complex NPCs governed by rudimentary artificial intelligence. These virtual worlds operate on fixed rules programmed by the developers' their own laws of physics. A character in a game like Grand Theft Auto or Red Dead Redemption cannot suddenly decide to defy the game's gravity or rendering engine. They are bound by its code. Now project this trend forward 1,000 or 1,000,000 years. Is it so difficult to imagine a civilization so advanced that its simulations are indistinguishable from reality, populated by conscious beings who believe their world is fundamental? Furthermore, some physicists point to potential glitches in the matrix, unexplained features of our own universe that could be interpreted as signs of a simulated construct. The strange, quantized nature of reality at the Planck scale, where space and time may be discrete rather than continuous, has been suggested as a possible sign of a finite resolution, much like the pixels on a screen. The seemingly arbitrary fine-tuning of the constants of nature could be seen as chosen parameters set by the programmers. Even the bizarre behavior of quantum particles, which remain in a state of probability until observed, has been likened to a rendering optimization technique, a way for the cosmic computer to save processing power by only calculating the precise details of a system when someone is looking at it. Yet, for all its fascinating allure, the simulation hypothesis faces powerful philosophical and scientific counterarguments. One of the most substantial is the sheer, mind-boggling computational burden of simulating an entire universe down to the quantum level for every single particle. Even if a post-human civilization had immense resources, simulating the conscious experiences of every human brain with perfect fidelity would require tracking the quantum states of billions of atoms in each brain, a task that might require a computer larger than the universe itself. This leads to the concept of patchy simulations worlds that are only rendered in high detail where observers are looking, like the loaded areas around a player character in a video game. But this itself creates a paradox. If the simulation is patchy, What happens when we build powerful microscopes or particle colliders that peer into the supposedly unrendered details? Would the programmers constantly be patching the simulation to cover their tracks? This begins to feel less like a rigorous scientific theory and more like an unfalsifiable modern myth, where any potential evidence against it can be explained away by the whims of the simulators. Another profound objection is the so-called problem of the real. If our reality is a simulation, then it must be running on something. That something, the computer and the civilization that built it, must exist in some higher, base reality that operates according to its own genuine physical laws. This simply kicks the ultimate question of existence up one level. How did that universe come to be? The simulation hypothesis doesn't answer the question of why there is something rather than nothing. It merely adds an extra layer of complexity to the mystery. This hypothesis, whether ultimately true or not, forces us to confront profound questions about the nature of reality, consciousness, and our place in the cosmos. It blurs the line between physics and metaphysics, between computation and existence. If we are in a simulation, do our lives have less meaning? Most philosophers would argue no. Our experiences of joy, love, curiosity, and pain are no less real to us whether they are generated by biological neurons or by lines of code on an alien supercomputer. The simulation argument ultimately serves as a powerful mirror, reflecting our own technological ambitions and our deepest existential anxieties back at us. It is a thought experiment that challenges us to define what we mean by real and pushes us to consider that the universe might not just be like a computation, but that existence itself might be a form of information processing all the way down, or perhaps all the way up. This relentless drive to decode reality, to find the source code, brings us back to the most reliable tool we have for this great unraveling, a language that seems to be woven into the very fabric of the cosmos. And so we find ourselves conscious observers within this grand computation, armed with a singular and breathtakingly powerful tool for deciphering it: mathematics. It is the lens through which we peer into the cosmic engine, the language we use to translate the silent, immutable laws of the universe into concepts our minds can grasp and manipulate. This is not a recent development, it is the very story of scientific progress. When Isaac Newton watched an apple fall and pondered the motion of the moon, he didn't just have a brilliant idea. He invented an entirely new form of mathematics, calculus, to describe the force of gravity quantitatively. The universe was already running its gravitational algorithm with perfect precision. Newton simply discovered the mathematical vocabulary it was using. The same pattern repeats throughout history. James Clerk Maxwell's equations didn't create electromagnetism. They revealed the elegant, symmetrical laws that light and radio waves had been obeying all along. The bizarre, non-commutative algebra of matrices turned out to be the native language of the quantum world, perfectly capturing the behavior of particles that defy classical logic. Every time we stumble upon a new mathematical structure, from the complex numbers that elegantly describe electrical circuits to the group theory that classifies the fundamental particles, it's as if we're finding another piece of the universe's source code, written in a language we are slowly learning to read. This uncanny alignment between the abstract world of mathematics and the concrete behavior of the physical world is so profound that it has left scientists and philosophers in awe for centuries. The physicist Eugene Wigner famously captured this astonishment in his essay on what he called the unreasonable effectiveness of mathematics in the natural sciences. He pointed out that mathematical concepts, often developed by mathematicians with no concern for practical application, purely for their own beauty and logical consistency, turn out to be inexplicably perfect for describing the laws of nature years or even centuries later. It feels like a miracle. Why should the intricate, imaginary landscapes of advanced algebra and differential geometry have anything to do with the spin of an electron or the curvature of spacetime? The most compelling explanation, one that resonates deeply with our theme, is that we are not inventing these mathematical relationships, we are discovering them. We are reverse engineering the universe's own operating system. Mathematics isn't just a human invention, it appears to be the native tongue of reality itself. The cosmos is a mathematical structure, and by doing mathematics, we are learning to speak its language, to understand the algorithms it has been running since the first moment of time. This journey of discovery is far from over. Each new mathematical insight opens up new horizons for exploring the cosmic computation. The quest to unify general relativity and quantum mechanics into a single theory of quantum gravity is at its heart a search for a new mathematics that can seamlessly describe both the vast, curved geometry of spacetime and the fuzzy, probabilistic world of the quantum. Theories like string theory and loop quantum gravity are, in essence, competing mathematical frameworks, each proposing a different set of equations that could be the ultimate algorithm from which all others derive. The fact that we are not yet sure which, if any, is correct doesn't diminish the power of the approach. It highlights that we are still learning the grammar and syntax of the cosmos's most fundamental language. Our ability to probe deeper than ever before is now being amplified by our own computational creations. We are beginning to build quantum computers, machines that harness the very principles of superposition and entanglement that underpin the universe's own processing. These aren't just faster calculators, they are entirely new kinds of instruments, like giving an astronomer a telescope that can see in a new color. With them, we might be able to simulate quantum systems directly, testing theories of quantum gravity in ways that were previously impossible, and perhaps even running small-scale models of cosmic processes to see what emerges. We are moving from being passive observers of the computation to active participants, building tools that allow us to experiment with the very fabric of reality in a laboratory. So where do we go from here? Our journey through the cosmos as a self-calculating system has brought us to the very edge of human understanding, but the map still has vast, blank territories marked "Here be dragons." The greatest of these uncharted regions is the glaring divide between our two most powerful descriptions of reality, the smooth, geometric curvature of Einstein's general relativity, which governs the very large, and the fuzzy, probabilistic dance of quantum mechanics, which governs the very small. Both are spectacularly successful in their own domains, but they speak entirely different mathematical languages and become mutually incomprehensible in extreme environments like the center of a black hole or the first moment of the Big Bang. Unifying them into a single, coherent theory of quantum gravity is the holy grail of modern physics, the essential next step in reading the universe's full source code. This isn't just an academic exercise, it's a necessary plunge into the unknown to complete our understanding of the cosmic computation. The leading contenders in this grand quest are some of the most mind-stretching concepts ever conceived. String theory, for instance, proposes that the fundamental building blocks of reality are not point-like particles but unimaginably tiny, vibrating loops of energy. In this view, an electron isn't a dot, it's a specific vibrational pattern on a string, much like a specific note played on a guitar string. The different vibrations of these strings would then correspond to all the different particles and forces we observe. The mathematics of string theory is breathtaking in its elegance, but it comes with a profound implication. For the equations to work, the universe must have more than the three spatial dimensions we experience. It requires extra curled-up dimensions, perhaps at every point in space, too small for us to perceive. This is a radical reimagining of the substrate of the cosmic computer, suggesting that the processing happens in a higher dimensional space, and our four-dimensional reality is a projection. Another compelling framework is loop quantum gravity, which takes a very different approach. Instead of adding dimensions, it focuses on the fabric of spacetime itself, proposing that it is not smooth and continuous but woven from a network of finite, discrete loops, a kind of spin foam. In this pixelated view, space is made of tiny, indivisible units of volume, and time is made of tiny, indivisible steps. There is no such thing as a distance smaller than the Planck length or a duration shorter than the Planck time. The universe computes its state by updating this spin network step by step, like a cosmic cellular automaton. This theory directly addresses the granularity of space and time, suggesting that the smooth geometry of general relativity is an emergent property, a large-scale average of these microscopic quantum loops. It's a vision of a universe that is fundamentally digital in its very essence. But how do we test these ideas? We cannot yet build a particle accelerator powerful enough to probe the Planck scale or peer directly into a black hole's singularity. This is where our own burgeoning computational power becomes our greatest ally. Scientists are now using massive supercomputers to run sophisticated simulations of the early universe, modeling how quantum fluctuations in the primordial fireball could have computed the large-scale structure of galaxies we see today. These cosmic simulations are like digital telescopes pointing back in time, allowing us to test different theories of quantum gravity by seeing which one, when used as the initial algorithm, produces a virtual universe that most closely matches our own. Even more tantalizing are the experiments being conducted with quantum computers themselves. These remarkable machines, which harness the principles of superposition and entanglement, are not just tools for calculation. They are miniature laboratories for creating and studying quantum systems. Physicists are now designing experiments to simulate the conditions near a black hole's event horizon, or to recreate the hypothesized quantum state of spacetime itself. By programming a quantum computer with the equations from loop quantum gravity or string theory, we might be able to watch these theories play out in a controlled, observable environment. It's a profound feedback loop. We are using small-scale quantum computations to help us understand the largest-scale quantum computation of all, the universe. A successful experiment might show us how information escapes a black hole or how spacetime emerges from a network of quantum relationships, providing the first experimental evidence for a theory of quantum gravity. The implications of this deeper understanding stretch far beyond pure science. Unlocking the principles of quantum gravity could revolutionize technology in ways we can barely imagine. It could pave the way for a true theory of quantum spacetime, giving us insights into the nature of wormholes or the possibility of warp drives, not as science fiction, but as extreme solutions to the equations of general relativity that might be stabilized by a proper quantum theory. More immediately, it could lead to new materials with exotic properties designed by manipulating matter at the most fundamental spacetime level. The deeper we read into the universe's source code, the more powerful our own programming abilities become. We are on the cusp of moving from merely observing the cosmic computation to potentially learning how to hack it, to harness the fundamental algorithms of reality for technologies that would seem like magic to us today. This is the ultimate promise of this quest, to finally answer the grandest question of all, not by finding a programmer, but by fully understanding the program that is, and has always been, running. So let's take a step back and see the breathtaking tapestry we've woven together. From the self-creating dance of a single cell to the gravitational choreography of entire galaxies, we've seen how autopoietic systems operate without a boss, guided only by their own internal, self-sustaining processes. This principle, born in biology, scales up to reveal a cosmos that is the ultimate self-maintaining entity, continuously regenerating its own structure from the bottom up. This isn't a universe that was built and then left to run down. It is a universe that is perpetually building itself, moment by computed moment. We then discovered that the language of this endless construction is mathematics. The mathematical universe hypothesis invites us to see every star, every atom, not as objects that obey mathematical laws, but as mathematical objects themselves. The equations we've painstakingly discovered aren't just descriptions, they are the very blueprints of existence. The cosmos is not a machine that calculates, it is the calculation itself, a dynamic, ongoing equation whose solutions are everything we see and experience. This mathematical structure finds its most active expression in the quantum realm, where particles exist as probabilities and the Schrödinger equation acts as the universe's master algorithm, computing possibilities into reality with every interaction, without a single decision made by an external hand. And from this quantum foundation, we witnessed the miracle of emergence, the stunning phenomenon where simple, local rules give rise to global complexity. The universe doesn't need a complex program to create a galaxy or a brain. It needs only a few basic laws of interaction, set in motion and allowed to compute over immense scales of space and time. This emergent complexity is powered and given direction by the relentless flow of entropy and information, a one-way street that provides the energy for every cosmic process and ensures that the computation always moves forward, carving the arrow of time itself into the fabric of reality. The fixed parameters of this computation, the fundamental constants, act as the immutable settings in the cosmic source code. They are the rules of the game, setting the stage for all possible interactions. And the force of gravity reveals itself not as a simple pull, but as the universe's mechanism for computing the very geometry of space-time, shaping the stage upon which everything else plays out. This computation is deterministic, yet wildly unpredictable due to the sensitive chaos of initial conditions, creating a future that is being written but not pre-written, full of novelty and genuine surprise. Life emerges as a magnificent subroutine within this grand computation, with DNA acting as a natural algorithm that computes organisms and evolution acting as a search algorithm that discovers new solutions. This expands into the philosophy of pancomputationalism, the view that every physical process, from a rock falling to a star burning, is a form of information processing. Our own consciousness appears as an emergent property of the brain's complex, integrated information processing, a localized knot of the universe's computation that has become aware of itself. This leads to the awe-inspiring possibility that the universe is a quantum computer, processing information in parallel across countless entangled qubits, with a capacity that dwarfs all human invention. The holographic principle suggests that this immense computation might be projected from a two-dimensional boundary, that our 3D reality is a magnificent illusion. And throughout it all, the deep symmetries of the cosmos, through Noether's theorem, generate the conserved quantities that provide the stability and consistency needed for such a long and intricate computation to unfold. Whether we consider the digital physics view of a pixelated spacetime or the multiverse theory of parallel computations, the picture is consistent, a reality that computes itself. The mysteries of dark matter and dark energy are the current frontiers, the unknown variables in the code that we have yet to decipher. the universe may even be engaged in a form of meta-computation, evolving its own laws through a process like cosmological natural selection, fine-tuning itself not for life, but for stability and fecundity. When we bring all these threads together, a coherent and magnificent picture emerges. We are not living in a clockwork universe wound up by a watchmaker. We are participants in a self-writing symphony, an epic, self-solving puzzle of unimaginable scale and complexity. There is no external programmer because the program and the output are one and the same. The laws are embedded, the processes are emergent, and the computation is autonomous. From the quantum foam to the cosmic web, the universe is a single, unified, and breathtakingly elegant process of self-calculation, a reality that is forever in the act of creating itself. So we've journeyed from the quantum haze where particles dance in a cloud of possibility to the vast cosmic web of galaxies, all bound by a single, breathtaking idea: the universe calculates itself. There is no external programmer, no cosmic coder writing lines in a language beyond our own. Instead, we find a reality built from self-creating processes, mathematical truths, and emergent complexity, all following a set of embedded rules that have been running since the very first moment. This isn't a cold, mechanical universe. It's a living, breathing computation of unimaginable scale, where the simple act of a particle choosing a path and the glorious spin of a galaxy are part of the same uninterrupted process. The laws of physics are the algorithm, and the unfolding of time is the output. This view of a self-calculating cosmos forces us to reconsider everything we thought we knew about our own place within it. If the universe is a deterministic computation, what does that mean for our free will? Are our choices truly our own, or are they simply the inevitable result of a chain of cause and effect that began billions of years ago? Perhaps the answer lies in the complex, emergent nature of consciousness itself. Our minds may be the universe's way of creating a localized point of view, a subjective experience within the grand calculation. Our free will might not be an illusion, but rather the experience of the universe computing the unique, intricate pattern that is us. We are not mere bystanders in this process. We are active participants, the cosmos becoming aware of its own existence, questioning its own nature, and striving to understand its own source code. It is a humbling and yet profoundly empowering realization. We are not separate from this majestic computation. We are a part of it. Every question we ask, every equation we solve, every telescope we point at the heavens is the universe turning its gaze inward. As the great Carl Sagan so beautifully put it, we are a way for the cosmos to know itself. Our curiosity is not a minor footnote in the grand scheme of things. It is the very purpose of the scheme. We are the mechanism by which the universe contemplates its own beauty, its own mystery, and its own origins. This journey doesn't end here. In fact, it has only just begun. The greatest mysteries, the true nature of dark matter and dark energy, the unification of quantum mechanics and gravity, the ultimate fate of our cosmic computation, are still waiting to be solved. And that solution will come from us, from our relentless drive to question, to explore, and to know. So keep wondering, look up at the night sky and see not just points of light, but the glowing nodes of a grand, interconnected calculation. Question the nature of your own consciousness and see it as the universe's most intimate and complex subroutine. We want to hear what you think. Does this idea of a self-calculating universe resonate with you? Does it change how you see your own place in reality? Share your thoughts, your questions, and your own theories in the comments below. Let's continue this incredible conversation together. And if you want to join us on more adventures into the deepest mysteries of space, time, and existence, please subscribe and hit the bell so you don't miss what comes next. Thank you for embarking on this intellectual adventure with us. The computation continues, and we can't wait to see